Assalamualaikum warahmatullahi wabarakatuh. Good day. On this cover slide, I will open our lecture on critical properties and real gases for the physical chemistry course. I would like you to prepare a careful and systematic way of thinking, because this topic is not only about writing formulas. It is about understanding how matter behaves in reality, especially when gases no longer follow the ideal gas picture. Please look at the main title on the slide, Critical Properties and Real Gases. These are two strongly connected ideas. Critical properties give us the key boundaries, and the key point, that explain when the distinction between a liquid and a gas starts to disappear. Real gases remind us of two fundamental physical facts: molecules have finite size, and molecules interact with each other. So, from the beginning, I want you to build one core intuition. When pressure becomes high, when temperature becomes low, or when you approach critical conditions, the assumptions of the ideal gas law start to break down. And precisely there, physical chemistry becomes very meaningful, because we learn how to choose the right model for the right conditions. Now I will introduce myself briefly, so you have a clear context about the instructor behind this lecture. My name is Dr. Heri Septya Kusuma. I am from the Department of Chemical Engineering, Faculty of Industrial Technology, Universitas Pembangunan Nasional Veteran Yogyakarta, Indonesia. In recent years, I have been listed in the top 2% scientist in the world by Stanford University and Elsevier BV specifically. For single-year impact, I was listed for the 2021 to 2022 period, the 2022 to 2023 period, the 2023 to 2024 period, and the 2024 to 2025 period, with national rankings in Indonesia that improved across those years. I was also listed for the career-long impact category. From a bibliometric perspective, my H-index is reported as 49 in Scopus, 42 in Web of Science, 52 in Google Scholar, and 50 in ResearchGate. I also serve as an editor for several journals, including Environmental Nanotechnology, Monitoring and Management, Food Physics, Journal of Chemical Research, and periodicals of Engineering and Natural Sciences. I am sharing this not as a formality, but to signal that the way I will guide you in this lecture is grounded in strong academic standards, and focused on correct conceptual understanding. Now, let me state the high-level goal of this lecture. After this session, you should be able to answer a very fundamental question: when can a gas be treated as ideal, when can it not, and how do we correct our calculations in a scientifically justified way? You should also understand what T sub C, P sub C, and V sub C mean, and why reduced properties and the compressibility factor Z become central tools for real gas calculations. I want you not only to compute, but also to explain, in your own words, why each correction makes physical sense. Let me also give you the structure of our learning path. We will start with motivation and evidence that real gases deviate from ideal behavior. Then we will move into the concept of the critical point through phase diagrams and P, V curves, so you truly understand what critical means physically. After that, we will lock in the definitions of critical properties, and then build the ideas of reduced properties and corresponding states. Next, we will discuss the compressibility factor Z, how to interpret it, and how to use it in calculations. Once that foundation is strong, we will step up to equations of state, such as the virial equation of state and the van der Waals equation of state, including the meaning of the parameters A and B, and how critical properties can be derived from critical point conditions. Finally, we will close with a summary, common conceptual traps, and practice problems so you are fully prepared to apply the concepts. Now, please do a quick readiness check. First, make sure you are comfortable with units and basic notation, such as Kelvin for temperature, and how to read subscripts consistently, for example T sub C and P sub C. Second, remember that in this lecture, I will often ask you to separate two things: what is mathematically correct, and what is physically reasonable. When those two are aligned, Your understanding is on the right track. So, the key message on this cover slide is simple. We will learn real gases in a systematic sequence, from physical intuition to correct calculation tools, with critical properties as a major conceptual pillar. Now, let us move to the next slide, where I will begin with the core idea, why real gases deviate, and how behavior near the critical point gives us a powerful window into the molecular reality behind the equations. Now we move from the cover slide into the first substantive idea of the lecture. On this slide, I want you to lock in two foundations that will control everything we do next. First, why real gases deviate from the ideal gas law. Second, what the critical point really means in terms of phase behavior and liquefaction. Let us begin with the equation that you already know very well, the ideal gas law. On this slide it is written as PV equals nRT. When I say it out loud, I want you to hear it as a compact model of reality, not as a universal truth. P times V equals N times R times T is a model that becomes accurate under certain conditions, but it has assumptions. And the slide gives you the key idea very clearly. Real gases deviate from PV equals nRT because molecules have, number 1, finite size, and number 2, intermolecular forces. Now, I want you to slow down and build intuition for each of these reasons, because later, when we introduce correction factors and equations of state, those corrections will be nothing more than mathematical ways of accounting for these two physical facts. First, finite molecular size. The ideal gas picture treats molecules as if they are point particles, meaning they occupy no volume at all. In that picture, the gas has the full container volume available for molecular motion. But in a real gas, molecules have a real, finite size. That means not all of the container volume is actually free volume for translation. Some portion is effectively excluded, because molecules themselves occupy space, and because two molecules cannot overlap. So, if you keep everything else the same and you start increasing pressure, you are pushing molecules closer together. The finite size effect becomes more important, because the fraction of excluded volume becomes significant compared to the total available volume. This is one reason why the ideal gas law begins to fail at high pressure. Second, intermolecular forces. The ideal gas picture assumes that molecules do not attract or repel each other, except during perfectly elastic collisions. But real molecules interact. In many practical conditions, there is an attractive component at intermediate distances, and a repulsive component at very short distances. Here is the key physical consequence. If attractions are significant, molecules pull each other slightly, and that can reduce the momentum transfer to the container wall compared with what the ideal model would predict. In other words, the measured pressure can be lower than the ideal gas prediction under the same temperature and volume, because attractions reduce the effective force on the wall. On the other hand, at very high density, repulsions and finite size dominate, and the pressure can become higher than the ideal gas prediction. So already, even without any new equation, you should be thinking like this: real gas deviation is not just one direction. The sign and magnitude of the deviation depend on which physical effect is dominating, and that depends on temperature and pressure. Now let us connect these molecular ideas to the second statement on the slide, which is about the critical point. The slide says, the critical point marks the end of the liquid-vapor boundary. Above T sub C, a gas cannot be liquefied by pressure alone. This is a very important statement, and I want you to internalize it carefully, because it is often misunderstood. What does it mean to liquefy a gas by pressure alone? It means you try to compress the gas, at a given temperature, and you hope that at some sufficiently high pressure it will condense into a liquid. The slide tells you that this strategy has a strict limit. There exists a critical temperature, T sub C. If the temperature is above T sub C, you can increase the pressure as much as you like, and you will not cross into a distinct liquid phase purely by compression. Instead, the material becomes what we call a supercritical fluid, where the traditional boundary between gas and liquid is no longer a sharp phase boundary. So, the critical point is not just a number on a table. It is a boundary in the logic of phase change. Below T sub C, compression can trigger liquefaction. Above T sub C, compression alone cannot. Now look to the right side of the slide. You see a historic set of P, V curves for CO2, attributed to Andrews, 1869, and the slide notes it is public domain. Even if you cannot read every label clearly, the main message is visible. It is a family of curves showing how pressure depends on volume under different conditions. This kind of figure is historically important because it gave early, strong experimental evidence for the existence of a critical point. What I want you to see conceptually is this. As conditions change, the shape of the P-V relationship changes in a way that reflects phase behavior. In some regions, the curve behavior indicates a transition where liquid and vapor can coexist, and as you approach the critical condition, that distinction fades until it disappears at the critical point. If any specific axis labels or temperature markings on this historic plot are not readable to you on the slide, that is fine. The key learning point here is not the exact numbers. The key learning point is that experimental P-V behavior is the origin of our critical point concept, and it is also the origin of why we need real gas models. Now, let me tie the two parts of the slide together in a single mental model. Real gases deviate from ideal behavior because of molecular size and molecular forces. Those same size and force effects are also exactly why liquefaction and phase boundaries exist in the first place. If molecules did not attract each other at all, the idea of a stable liquid phase would not arise in the same way. So, the critical point is not an isolated topic. It is a direct consequence of intermolecular interactions. That is why this lecture puts critical properties and real gases in one connected storyline. At this stage, I want you to do a quick understanding checkpoint. First, can you say, in one sentence, the two physical reasons for deviation from PV equals nRT? You should be able to say, finite molecular size, and intermolecular forces. Second, can you explain the meaning of the critical point in one clear statement, without using vague words? You should be able to say, the critical point is the end of the liquid-vapor boundary, and above T sub C, liquefaction cannot be achieved by pressure alone. Third, can you predict, at least qualitatively, when you expect the ideal gas law to work better? Even before seeing any graphs or correction factors, you should suspect that low pressure and sufficiently high temperature usually reduce the importance of size and interaction effects. Let me summarize this slide in a few sentences. This slide gives you the physical origin of real gas behavior. Molecules are not points, and they do not ignore each other. It also gives you the physical meaning of the critical point. It is the termination of the liquid-vapor boundary, and it introduces the critical temperature T sub C as a limit for pressure-driven liquefaction. If you understand these two messages, you already have the conceptual backbone for everything we will do later with compressibility factors and equations of state. Now, let us transition to the next slide. Next, I will formalize what you are expected to learn in this lecture, and I will show you the roadmap, so you know exactly where critical properties appear, where real gas corrections appear, and how each slide will build on the previous one in a logical sequence. Now we proceed to this slide, which is the learning goals slide. This slide is very important, because it tells you what you should be able to do, not only what you should be able to memorize. So, as we go through the lecture, I want you to keep returning mentally to these goals and checking, can I actually do this yet, in my own words and with correct reasoning? Let me connect this slide to the previous one. On the previous slide, we established two core physical reasons why real gases deviate from the ideal gas law, P times V equals N times R times T, finite molecular size and intermolecular forces. We also introduced the critical point as the end of the liquid, vapor boundary, and we emphasized that above T sub C, a gas cannot be liquefied by pressure alone. So, today's lecture is not a random collection of facts. It is a controlled learning path that starts from physical reality and ends with practical calculation tools. Now, I will read the left panel first, because it states what you should be able to do by the end of this lecture. The slide says, by the end of this lecture, students can, and then it lists several items. I will go one by one, but I will also explain what each item really means in practice. The first goal says, state when the ideal gas law is reliable, low P, high T. This is not just a slogan. This is a decision rule. It means, given a real situation, you should be able to judge whether the ideal gas law is a reasonable approximation. The phrase low P, high T is a compact way of saying, when pressure is low, molecules are far apart, so finite size effects are small, and when temperature is high, thermal motion tends to reduce the relative impact of attractions, so intermolecular force effects are smaller. So you should learn to connect the rule to the molecular reasoning, not just repeat the rule. The second goal says, define critical constants, T sub C, P sub C, and V sub C. Here, define means you should be able to state clearly what each quantity represents physically, and where it comes from in phase behavior. For example, T sub C is not just a temperature. It is the critical temperature at which the liquid, vapor boundary terminates. P sub C is the pressure at the critical point. V sub C, or critical molar volume, is the molar volume at that same critical point. Later, we will see why these constants become very useful for creating reduced variables that allow different substances to be compared on a common scale. The third goal says, interpret real fluid P, V isotherms and the critical point. This is a skill goal. It means, if I show you a plot of pressure versus volume at constant temperature, you should be able to explain what the shape means, where the two-phase region is, how the curve changes as temperature changes, and what special features appear at the critical condition. The key word here is interpret. That means, connect what you see to phase behavior and molecular interactions, not just describe the picture. The fourth goal says, use Z equals PV sub M over RT to quantify non-ideality and correct PV equals nRT. This is where we move from qualitative understanding to quantitative correction. Z is the compressibility factor. It measures how far the real gas is from ideal behavior under given conditions. If Z equals 1, the gas behaves ideally in that condition. If Z is not 1, then you correct the ideal gas relation by writing PV equals Z times N times R times T. I want you to see that this is not a new law, it is a correction framework built on the same structure, but with a physically meaningful factor that captures deviation. The fifth goal says, explain where virial and van der Waals equation of state come from, assumptions plus steps. This is a very important goal, because it forces you to understand origin and logic, not only final formulas. When the slide says assumptions plus steps, it means you should be able to tell the story of the derivation. For virial, you should understand it as an expansion that works in certain limits, and how the coefficients relate to interactions. For van der Waals, you should understand the two core corrections, a volume correction linked to finite molecular size, and a pressure correction linked to attractions. If you can explain those assumptions and how they lead to the final equation, you are thinking like a physical chemist, not like a formula collector. Now, move your attention to the right panel, titled Roadmap. This is the sequence we will follow, and I want you to treat it like a navigation guide during the lecture. Number 1, why ideal gas fails. That is what we started already, finite size and intermolecular forces. We will still expand this idea with more concrete phase reasoning. Number 2, phase behavior. This is where we connect gases to liquids, and we make sure you understand what phase boundaries mean, because critical properties are not meaningful unless you understand phase behavior. Number 3, critical point. We will zoom in on the critical point and make it precise, what it means on P, T and P, V diagrams, and what changes physically at that condition. Number 4, Z factor. This is our first major calculation tool. We will define it, interpret it, and learn how to use it to correct calculations. Number 5, virial equation of state. This will give you a more theory-grounded way to represent deviations, especially at low to moderate densities. Number 6, van der Waals equation of state. This will give you a classic, physically motivated model, and it will also allow us to talk about how an equation of state can predict critical constants. Number 7, critical constants. Here we will connect the dots, how critical constants appear, how they can be derived in certain models, and how they support corresponding states thinking. Number 8, example plus practice. This is where you will see the lecture become operational. You will compare ideal and real gas predictions, and you will practice using the correct tools in the correct conditions. Now, let me do a short checkpoint with you. After seeing this slide, you should be able to answer this: what are the three main pillars of today's lecture? The first pillar is phase and critical behavior. The second pillar is quantifying non-ideality using Z. The third pillar is equations of state, especially virial and van der Waals, and understanding where they come from. If you can keep those pillars in mind, the lecture will feel coherent and not fragmented. Let me summarize this slide. This slide sets the target outcomes and the path to reach them. You are expected to make judgments about when ideal gas behavior is reliable, define critical constants, interpret real fluid P, V isotherms, use Z to correct calculations, and explain the origins of virial and van der Waals equations of state with their assumptions and steps. Now we are ready to move forward. In the next slide, we will begin the technical content by sharpening the contrast between the ideal gas model and the real gas reality. I will guide you to see exactly which assumptions break first, and why those assumptions are connected to the phase behavior we are about to discuss. Now we proceed to the slide, titled Ideal vs Real Gases. This slide is a bridge. It takes the key idea from earlier, that real gases deviate because of finite size and intermolecular forces, and it turns that idea into a clear, testable comparison between an ideal model and what actually happens in real molecular systems. By the end of the slide, you should be able to do two things. First, you should be able to state the assumptions behind the ideal gas model. Second, you should be able to predict, qualitatively, how real gas behavior will differ when attractions dominate versus when crowding dominates. Let us start on the left side, under the heading Ideal Gas Model Assumes. There are 3 bullet points here, and I want you to treat them like the terms and conditions of the ideal gas law. The first assumption says, molecules have negligible volume, meaning they are treated as point particles. This is not just a mathematical convenience. It is a physical claim. It says the molecule itself does not take up space in any meaningful way compared with the container volume available for motion. So, in the ideal picture, the entire container volume is available for molecular translation. The second assumption says, no attractions or repulsions except during collisions. This is extremely important. It says molecules do not feel each other at a distance. They only interact when they collide, and those collisions are treated as instantaneous and elastic. So between collisions, molecules move freely, and their trajectories are not bent by forces from neighbors. Now look at the third statement, therefore, PV equals nRT works best at low P and high T. This is not a new assumption. It is a consequence. Let me explain the logic. At low pressure, the gas is dilute, meaning molecules are far apart, so the finite size assumption is less wrong, and the force-free assumption is less wrong, because attractions and repulsions decrease rapidly with separation. At high temperature, molecules have higher kinetic energy, so attractions become relatively less significant compared with thermal motion. So the ideal gas law becomes a better approximation. Please remember, this is exactly the same reasoning that we introduced earlier, but now it is organized as a model statement. Now move to the right side, titled Real Gas, What Actually Happens. Here the slide is giving you a visual intuition using two small schematic panels labeled A and B, with ideal and real shown side by side. I want you to use these pictures as a mental shortcut, but also understand the physics behind them. In panel A, you see an ideal box and a real box. In the ideal box, the particles are spaced and there are no arrows indicating forces. In the real box, you see arrows around a particle that suggest it is experiencing forces from neighbors. This corresponds to intermolecular interactions. The main lesson is that, in a real gas, molecules do not only collide. They also exert forces on each other while they are separated. Those forces can change the effective pressure you measure, because pressure is ultimately a result of momentum transfer to the wall. If attractive forces reduce how strongly molecules hit the wall, then the measured pressure can be lower than the ideal prediction at the same volume and temperature. In panel B, again you see ideal and real, but now the crowding looks more significant. The point is that at higher pressure, the finite molecular size becomes important. When the gas is compressed, molecules are packed closer together. The excluded volume becomes a significant fraction of the total container volume. In that case, the ideal assumption of point particles fails strongly. And when you try to compress further, repulsive effects and excluded volume make the pressure rise more steeply than the ideal model would suggest. Now read the text at the bottom of the right panel, because it gives the direction of the effects explicitly. It says, attractions reduce measured pressure, weaker wall impacts, and can reduce volume at fixed P. I want you to interpret this carefully. Reduce measured pressure means, if you compare real gas and ideal gas at the same temperature and volume, attractions can make the real measured pressure lower than P predicted by nRT over V. Another way to view it is, at a fixed pressure and temperature, attractions can pull molecules closer, effectively reducing the volume compared with what the ideal model would predict. So, attraction can make the gas more compressible than ideal in that regime. Then the slide says, finite molecular size becomes important at high pressure, crowding. This is the other regime. When crowding dominates, the gas becomes less compressible than ideal, because you cannot pack point particles indefinitely. Real molecules occupy volume, and strong repulsions appear at short distances. So, in that regime, the real pressure can become higher than the ideal prediction under the same conditions. Now I want you to connect this slide to the roadmap we saw earlier. This slide is the beginning of the roadmap item why ideal gas fails. And it also prepares you for later tools, especially the compressibility factor Z. Why? Because Z is essentially a way to express, numerically, the kind of deviations we are describing qualitatively here. When attractions dominate, you often find Z less than 1. When repulsions and excluded volume dominate, you often find Z greater than 1. I am not asking you to memorize that as a universal rule right now, but I want you to see that this slide is planting the physical meaning that will later be encoded into Z. Now let us do a checkpoint. First, can you list the two core assumptions of the ideal gas model, without looking? You should be able to say, point particles with negligible volume, and no intermolecular forces except during collisions. Second, can you predict what happens to measured pressure when attractions are important? You should be able to say, measured pressure can be lower than the ideal prediction, because attractions weaken wall impacts. Third, can you predict what happens at high pressure when molecules are crowded? You should be able to say, finite size and repulsions become important, and the ideal model becomes unreliable. Let me summarize this slide. The ideal gas model assumes point particles and no long-range interactions, which is why PV equals nRT works best at low pressure and high temperature. Real gases violate both assumptions. Attractions can reduce measured pressure and increase compressibility in certain regimes, while finite molecular size becomes critical at high pressure, making the gas less compressible than ideal. Now we transition to the next slide. Next, we will move from this qualitative comparison into phase behavior, because the most dramatic consequences of intermolecular forces are not only deviations in pressure. They are the existence of liquids, phase boundaries, and ultimately the critical point that we will analyze carefully. Now we proceed to slide 5, titled Why We Care, where real gas effects matter. This slide answers a very practical question that many students quietly have in their mind, which is, why should I spend time learning real gas models, critical properties, and equations of state, if the ideal gas law is so simple and so familiar? By the end of this slide, you should be able to explain, in a clear and convincing way, where the ideal gas assumption becomes risky, and why real gas thinking is not optional in certain applications. Let me connect this slide to the previous one. In the last slide, we compared ideal versus real gases. We said the ideal model assumes point particles and no intermolecular forces except during collisions. We also said real gases deviate because molecules have finite size and intermolecular forces. What this slide does is take that conceptual difference and translate it into engineering and physical chemistry consequences. In other words, this slide is telling you, here is where the small conceptual error becomes a large practical error. Now, before we read the bullet points, I want you to adopt one guiding principle. In physical chemistry, a model is not judged by how beautiful the equation is. A model is judged by whether it is accurate enough for the condition you are studying, and whether it supports correct decisions. So, when you hear real gas model, think, this is a tool for avoiding wrong decisions about pressure, volume, density, and phase. Now let us read the main heading on the slide. It says, real gas models are essential for, and then it lists 4 major contexts. I will take each one and explain the physical reason behind it, because that is the part you must understand. First, the slide says, liquefaction, refrigeration cycles, and cryogenics, near phase change. Please focus on the phrase near phase change. Why is that the danger zone? Because near phase change, the gas is no longer a very dilute collection of molecules. Density increases, molecules are closer, and intermolecular attractions become strong enough to create a condensed phase. In that region, the ideal gas law is not only slightly inaccurate. It can become qualitatively misleading, because it does not know that a phase boundary exists. So, in liquefaction and refrigeration, you often operate in regions where a vapor is close to condensing, or a liquid is close to boiling. The behavior of pressure and volume there is dominated by real molecular interactions. If you pretend the vapor is ideal, you can misestimate properties that control cycle performance, such as the relation between pressure and density, or how compression moves the state closer to condensation. In cryogenics, the same logic is even stronger, because temperatures can be low relative to the substance's critical temperature. T sub C low temperature makes attractive forces more influential compared with thermal motion. So the system becomes strongly non-ideal. Second, the slide says, high-pressure reactors and pipelines, PVT accuracy. I want you to read PVT as pressure, volume, temperature. In high-pressure systems, the core issue is density. For gases, density is the bridge between what you measure and what you need for design. If you are designing a pipeline or a reactor, you care about how much mass is inside, how the mass flow relates to volumetric flow, and how compressibility affects pressure drop and storage capacity. At high pressure, molecules are forced close together. That means finite size effects and repulsions matter, and attractions can also matter depending on temperature. So, the ideal prediction for volume or pressure at a given amount of gas can be significantly off. In a pipeline context, that can propagate into errors in sizing, operational limits, and safety margins. The main message is simple. When pressure is high, you must treat the gas as real, because the gas is no longer gas-like in the ideal sense. Third, the slide says, gas storage and compression, safety plus sizing. This one is very straightforward, and it is a perfect example of why real gas behavior matters. When you store gas in a cylinder or compress gas in a compressor, you are making decisions based on how pressure relates to amount of gas and volume. If you assume ideal behavior, you might miscalculate how much gas is actually stored at a given pressure, or how the pressure changes as you compress. In safety terms, pressure is not just a number. It is a load on equipment. In sizing terms, volume and density determine capacity. So even a moderate deviation from ideal behavior can matter, because it affects whether your design meets its target and whether it remains within safe limits. Here I want you to remember the mental picture from the previous slide. At high pressure, crowding becomes important, and the gas can become less compressible than ideal. If you forget that, you might underestimate pressure rises during compression, or misunderstand how much free volume is effectively available. Fourth, the slide says, supercritical applications, for example supercritical CO2 extraction. This bullet connects directly to our critical properties theme. A supercritical fluid exists when the temperature is above T sub C and the pressure is above P sub C. In that region, the distinction between liquid and gas disappears, but the fluid can have properties that are intermediate, such as gas-like ability to diffuse and liquid-like ability to dissolve certain substances. That is exactly why supercritical CO2 is used in extraction processes. But notice the key point. The whole concept of supercritical does not even exist in ideal gas thinking. Ideal gas has no phase boundary, so it has no critical point and no supercritical region. So if you are studying or designing supercritical processes, real fluid behavior is not just important. It is the entire foundation of the process. Now, look at the blue box at the bottom of the slide. It states a rule of thumb: deviations grow as you approach condensation, near T sub C, and or increase pressure. I want you to treat this sentence as a practical alarm bell. Let us unpack it slowly, because this is one of the most useful heuristics you will take from this lecture. First part, deviations grow as you approach condensation. Condensation means vapor is turning into liquid. Physically, that happens when attractive forces successfully bring molecules together into a dense phase. So near condensation, intermolecular attractions are no longer small perturbations. They are dominant. That is why the ideal gas assumption becomes weak there. Second part, near T sub C. The critical temperature, T sub C, is a marker of the strength of intermolecular forces for a given substance. When you are near critical conditions, the system is extremely sensitive. Small changes in pressure or temperature can produce large changes in density and compressibility. That means any model that ignores intermolecular forces will struggle to represent that sensitivity. So, near T sub C, you should expect strong non-ideality and you should be cautious. Third part, and or increased pressure. This is the crowding argument. High pressure pushes molecules close, increasing density. As density increases, both finite size effects and interaction effects become more important. So, even if temperature is not extremely low, sufficiently high pressure can still produce strong non-ideal behavior. Now, I want you to form a simple decision process in your mind. When you are given a gas problem, before you calculate anything, ask yourself two questions. First, is the pressure low enough that the gas is dilute? Second, is the temperature high enough that attractions are relatively weak and I am far from condensation and far from T sub C? If the answer to both is yes, the ideal gas law is often reliable. If the answer to either is no, you should immediately consider real gas corrections, such as the compressibility factor Z, or an equation of state. Let me also address a common misconception that can appear here. Some students think, real gas models are only for extremely high pressure. That is not correct. The slide is reminding you that proximity to condensation and proximity to the critical region can also drive strong deviations, even if the pressure is not what you personally consider extreme. The key is not a single pressure value. The key is the combined condition, pressure, temperature, and closeness to phase change. Now let us do a checkpoint. I want you to test your understanding in a practical way. If I say refrigeration cycle near phase change, what is your immediate reasoning? You should say, near phase change, interactions matter strongly, ideal gas is risky, real gas models are important. If I say high pressure pipeline, what is your immediate reasoning? You should say, high pressure increases density, crowding and interactions matter, I need PVT accuracy, so I should use real gas methods. If I say supercritical CO2 extraction, what is your immediate reasoning? You should say, supercritical region is defined by critical properties, ideal gas cannot represent it, real fluid behavior is essential. Now I will give you a short mini summary of this slide. This slide explains the motivation. Real gas models are essential whenever you operate near phase change, near critical conditions, and/or at high pressure. These conditions appear in liquefaction, refrigeration, cryogenics, high-pressure reactors and pipelines, gas storage and compression, and supercritical applications such as supercritical CO2 extraction. The rule of thumb is clear, deviations from ideal behavior grow as you approach condensation, near T sub C, and as you increase pressure. Now we transition to the next slide. Next, we will start building the phase behavior framework more explicitly. That means we will move from where real gas effects matter into how phase behavior is organized, so that critical point and critical properties become precise concepts rather than just words. In the next slide, I will guide you to see how the phase boundary is represented and how the critical point sits at the end of the liquid-vapor boundary. Now we proceed to slide 6, titled Phase Behavior Refresher, P.T. diagram. This slide is a refresher, but it is not a small slide. It is foundational, because the critical point is not truly understood unless you can locate it correctly on a phase diagram, and unless you know what a phase boundary actually represents. By the end of the slide, you should be able to do 3 things. First, you should be able to explain what a P.T. phase diagram tells you. Second, you should be able to interpret the meaning of the boundary lines and special points. Third, you should be able to explain why the liquid-vapor boundary ends at the critical point, and what supercritical means on this diagram. Let me connect the slide to the previous one. The previous slide answered why we care, and it emphasized that real gas deviations grow near condensation, near T sub C, and at high pressure. This slide now gives you the map that shows where condensation and critical conditions live. So, conceptually, we are moving from motivation to structure. Now, look at the left panel under Key Ideas. The first bullet says, a phase diagram shows which phase is stable at a given pressure and temperature. Please notice the word stable. It means, if you set a system at that pressure and temperature and let it reach equilibrium, the phase shown in that region is the one that persists. So, a phase diagram is not a picture of what you happen to see at one moment. It is an equilibrium map. The second bullet says, lines are phase boundaries, where 2 phases are in equilibrium. This statement is extremely important. A boundary line on a P.T. diagram is not just a separator. It represents coexistence of 2 phases at equilibrium. For example, on the liquid-vapor boundary, liquid water and water vapor can coexist at the same pressure and temperature, as long as the system is at equilibrium. This is also why the line is sometimes called a coexistence curve. The third bullet says, the liquid-vapor boundary ends at the critical point. This is the heart of our lecture. The idea is that the coexistence between a distinct liquid phase and a distinct vapor phase has a terminal point, beyond which the distinction disappears. So, as you move along the liquid-vapor boundary to higher temperature and higher pressure, you approach a point where the properties of the liquid and the properties of the vapor become the same in a continuous way. The fourth bullet says, above the critical point, there is a single supercritical phase, with no distinct liquid versus vapor. This is the major conceptual jump. It means, once you are above the critical point, you cannot talk about boiling or condensation in the same way, because there is no phase boundary to cross between liquid and gas. Instead, the fluid changes continuously with P and T, but it remains a single phase. Now, move to the right panel, which gives an example using water. This diagram is schematic, but it is rich enough for us to practice interpretation. On the vertical axis you see pressure, labeled in kilopascal. On the horizontal axis you see temperature in degrees Celsius. The diagram shows three main regions: ice, meaning solid, water, meaning liquid, and water vapor, meaning gas. And it highlights two special points, the triple point and the critical point. Let us interpret it slowly. First, the regions. If you pick any point inside the water vapor region, the stable phase at equilibrium is vapor. If you pick a point inside the water liquid region, the stable phase is liquid. If you pick a point inside the ice solid region, the stable phase is solid. That is the simplest way to use a phase diagram. Given P and T, you locate the point and read the stable phase. Now, the boundary lines. The curved boundary between liquid and vapor is the liquid-vapor coexistence curve. Along that curve, liquid water and water vapor can coexist in equilibrium. The boundary between solid and liquid is the melting or fusion line. The boundary between solid and vapor is the sublimation line. Now look at the triple point. It is labeled triple point. The triple point is where three phase boundaries meet. Conceptually, it is where solid, liquid, and vapor can all coexist in equilibrium at a unique pressure and temperature. On this diagram, the triple point is shown near 0 degrees Celsius and very low pressure, around 0.6 kilopascal. I want you to treat the exact number as a reference, but the essential meaning is, triple point is the unique condition where all three phases can coexist. Now look at the critical point. It is labeled critical point at the upper right end of the liquid-vapor boundary. The diagram shows an approximate temperature around 374 degrees Celsius, and a pressure around 22,089 kilopascal. Again, treat the exact values as context, but the conceptual meaning is the key. This point is the end of the liquid-vapor coexistence curve. That is why the curve stops. It does not continue forever. At this point, there is no longer a distinct boundary separating liquid from vapor. Now, I want you to connect this diagram to the statement we made earlier, above T sub C, a gas cannot be liquefied by pressure alone. How does the diagram show that? Imagine you choose a temperature to the right of the critical temperature, meaning greater than T sub C. That means you are to the right side of the critical point on the horizontal axis. Now, if you increase pressure at that temperature, you move vertically upward. Do you cross a liquid-vapor boundary? No, because the boundary line ends at the critical point and does not extend to higher temperatures. So, you remain in a single-phase region. That is the diagrammatic proof of the statement. Above T sub C, there is no line to cross into a separate liquid phase. That is why pressure alone cannot liquefy the gas. Now, one more subtle but important idea. Students often think supercritical means high pressure. But that is incomplete. Supercritical means you are above both the critical temperature and the critical pressure, meaning you are beyond the critical point region. It is defined relative to the critical constants. So, supercritical is not a vague descriptor. It is a state defined by P and T relative to P sub C and T sub C. Now let us do a checkpoint. I want you to test yourself with 3 quick tasks. First, if I give you a pressure and temperature, can you explain how to determine the stable phase using this diagram? Second, can you explain what it means to be on a boundary line, in terms of phase coexistence? Third, can you explain, using the diagram, why above the critical temperature there is no liquefaction by pressure alone? If you can do these 3 tasks, then you are ready for the next step, which is connecting phase behavior to P, V behavior, because critical properties also appear very clearly on P, V isotherms. Let me summarize this slide. A P-T phase diagram is an equilibrium map of stable phases. Boundary lines represent 2-phase equilibrium. The liquid-vapor boundary terminates at the critical point, and above the critical point the system exists as a single supercritical phase without a distinct liquid versus vapor boundary. The water example illustrates the triple point, where 3 phases coexist, and the critical point, where the liquid-vapor boundary ends. Now we transition to the next slide. Next, we will shift from the P-T diagram to P-V isotherms, because that is where you will see, more directly, how pressure changes with volume at different temperatures, how the 2-phase region appears, and how the shape of the curve changes as you approach T sub C. This will prepare you to define critical constants precisely and later to introduce the compressibility factors E. Now we proceed to slide 7, titled P-V isotherms for a real fluid. This slide is extremely important because it shows you, visually and physically, what the critical point means on a pressure-volume curve, not only on a pressure-temperature diagram. By the end of the slide, you should be able to read a family of P-V curves correctly, and you should be able to explain what changes when temperature is below T sub C, exactly at T sub C, and above T sub C. Let me connect this to the previous slide. Previously, we used a P-T phase diagram to see that the liquid-vapor boundary ends at the critical point, and that above the critical point there is a single supercritical phase. Now, the P-V representation gives you a different viewpoint. Instead of asking, which phase is stable at this P and T, we ask, if temperature is fixed, how does pressure respond as volume changes, and what does that tell us about phase coexistence? This is the viewpoint that historically led to critical point understanding through experiments like those of Andrews. Now, I will follow the structure on the slide. The left panel is titled How to Read These Curves. I want you to treat the left panel as your reading guide, and the right panel as your example. First sentence, each curve is an isotherm, meaning constant temperature. That is the meaning of isotherm. So, if you see multiple curves, each one corresponds to a different temperature value, but within one curve, temperature is fixed. Now, the slide divides interpretation into 3 regimes. This is exactly the structure you must remember. Regime 1, for T less than T sub C. The slide says, a flat or near flat segment appears, which indicates liquid-vapor coexistence, meaning 2 phases. Let me explain the logic carefully. At T below the critical temperature, there exists a range of volumes where the system does not remain a single uniform phase when you compress it. Instead, it separates into 2 phases, liquid and vapor, in equilibrium. In that region, you can change the overall volume by changing the relative amounts of liquid and vapor, while the pressure stays approximately constant. That is why the P-V curve shows a flat or nearly flat plateau. The pressure is essentially the saturation pressure at that temperature, while the volume changes because the fraction of vapor versus liquid changes. So, the plateau is a signature of 2-phase equilibrium on a P-V isotherm. Regime 2, at T equals T sub C. The slide says, the curve has an inflection point, which is the critical point. This is subtle but central. At the critical temperature, the two-phase plateau shrinks until it disappears into a single point. At that special point, the curve transitions smoothly without a flat coexistence region, but it has a point of inflection, meaning the curvature changes sign. In more physical terms, the system is at the boundary where liquid and vapor become indistinguishable. On the P-V curve, the critical point is where the distinction between the liquid side and the vapor side collapses into one state. So the critical point can be identified by the special shape of the isotherm at T sub C. Regime 3, for T greater than T sub C. The slide says, no two-phase plateau, therefore single supercritical fluid. This is exactly consistent with the P-T phase diagram. Above T sub C, there is no liquid-vapor coexistence line to cross. So, as you compress the fluid at constant temperature above T sub C, pressure changes continuously with volume, and the system remains a single phase. In this regime, we often call it a supercritical fluid when pressure is also sufficiently high, but the key point on the P-V curve is, there is no flat segment indicating phase separation. Everything is continuous. Now, let us move to the right panel, the example, CO2, Andrews isotherms. This is an historic experimental style plot. Let us read it carefully, but also safely, because some labels are small. I want you to focus on what is clearly visible and conceptually reliable. First, observe the axis. The vertical axis is pressure, labeled in atmosphere. The horizontal axis is molar volume, labeled in milliliter per mole. This is important, because it immediately reminds you that molar volume, V sub m, is a natural variable for equations of state and for compressibility analysis later. Next, observe that multiple isotherms are shown, with temperatures labeled near the top region, such as 13.1 degrees Celsius, 21.5 degrees Celsius, 31.0 degrees Celsius, 32.5 degrees Celsius, and 48.0 degrees Celsius. The slide also highlights the phrase temperatura critica, indicating the critical temperature region. Even if you do not read every label perfectly, you can clearly see that the curves change character as temperature changes. Now, look for the region labeled liquid and vapor in equilibrium. You can see a shaded area in the middle lower part of the plot, indicating coexistence of liquid and vapor. This shaded region corresponds exactly to the plateau behavior discussed on the left panel for T less than T sub C. It is the region where two phases coexist, and the system's overall state is not described by a single uniform phase. On the left side of the diagram, there is a region labeled liquid, and on the right side there is a region labeled vapor. This is consistent. At small molar volume you have a dense liquid-like state, and at large molar volume you have a gas-like state. In between, for temperatures below T sub C, the system can separate into liquid plus vapor. Now, locate the label critical point or punt critic, and also isoderma critica, meaning the critical isotherm. These labels indicate that one particular isotherm corresponds to the critical temperature. At that isotherm, the curve passes through the critical point, and the shape is special. The plateau has collapsed, and the curve shows a distinctive flattening and inflection around that point. There is also a label for critical pressure, shown as approximately 72.8 atmosphere. Again, the exact number is not what I want you to memorize from this slide, but I want you to see the idea. The critical point has a specific pressure value, P sub C, and a specific molar volume value, V sub C. In fact, near the bottom, you can see a value around 94.2 milliliter per mole, associated with critical molar volume. The slide itself tells you to note the critical temperature and critical point labels, so the goal is recognition and interpretation, not memorization of all numerical details. Now, I want you to connect this to a deep conceptual idea. On the P-T diagram, the critical point is the end of a line. On the P V diagram, the critical point is a special point on a curve, specifically on the critical isotherm, characterized by an inflection. So, the same physical reality appears in two graphical languages. If you can translate between these two, your understanding becomes robust. Now let us do a checkpoint. I want you to imagine 3 experiments at constant temperature, where you slowly compress a substance and observe pressure as volume decreases. First experiment, T is below T sub C. What should you expect? You should expect that at some point, instead of pressure rising smoothly, you will enter a two-phase region where pressure stays roughly constant while the system becomes a mixture of liquid and vapor. That is the plateau. Second experiment, T equals T sub C. What should you expect? You should expect that the two-phase plateau has just disappeared, and the curve shows a special critical shape with an inflection at the critical point. Third experiment, T is above T sub C. What should you expect? You should expect no plateau and no phase separation. Pressure increases continuously as volume decreases, and the system remains a single phase. If you can describe these 3 outcomes clearly, you have mastered the core reading skill for P, V isotherms. Let me summarize this slide. Each curve is a constant temperature P, V isotherm. For temperature below T sub C, a flat or near flat segment appears, indicating liquid, vapor coexistence, meaning 2 phases in equilibrium. At temperature equal to T sub C, the isotherm contains an inflection point that defines the critical point. For temperature above T sub C, there is no two-phase plateau, and the behavior is continuous, corresponding to a single supercritical fluid region in the appropriate conditions. Now we transition to the next slide. Next, we will deepen the physical meaning of the critical point and connect it explicitly to the idea that liquid and vapor become indistinguishable, and then we will formalize the definitions of critical constants, T sub C, P sub C, and V sub C, which will later allow us to introduce reduced properties and the compressibility factor Z. Now we proceed to slide 8, titled The Critical Point, Physical Meaning. This slide is where I want you to shift from diagram reading to physical understanding. On the previous slide, we learned how P, V isotherms behave below T sub C, at T sub C, and above T sub C, and we used that to identify the critical point as an inflection point on the critical isotherm. Now, on this slide, I want you to understand what actually changes in the material at that critical condition, and why the boundary between liquid and vapor truly ends. Let us start with the left panel, under the question, what changes at the critical point? Please read the first bullet carefully. At the critical point, liquid and vapor become indistinguishable. This sentence is often repeated, but I want you to understand it precisely. Indistinguishable means there is no measurable, sharp difference that allows you to say, this side is liquid and that side is vapor, when the system is at the critical point. In subcritical conditions, you can clearly see a liquid phase with high density and a vapor phase with low density, separated by an interface. At the critical point, the densities of the two phases converge to the same value. When the density difference goes to 0, the phases are no longer distinct phases. And if there is no distinct phase difference, there is no reason for an interface to exist. Now read the second bullet, the liquid-vapor boundary ends, meaning no surface separating phases. This is a direct physical consequence. In a two-phase system, the interface exists because two phases with different properties coexist. If the properties become identical at the critical point, the interface loses meaning. So, you should think of the critical point as the termination of the idea of boiling as a phase boundary phenomenon. Above that point, you can still have density changes and property changes, but they occur continuously without a phase boundary. Now, the slide has a subheading, above T sub C. There are two bullets here, and both are essential. The first bullet says, increasing pressure alone cannot liquefy the fluid. We already supported this statement using the P-T phase diagram, and we also supported it using the absence of a two-phase plateau above T sub C on P-V isotherms. Now you should also understand the physical reason. There is no separate liquid phase available to enter by compression, because above the critical point the system remains one phase. Compression changes density, but it does not create a distinct liquid phase separated by an interface. The second bullet says, the fluid is supercritical, and its properties are between gas-like and liquid-like. This is an important idea, but we must be careful with interpretation. Between does not mean the fluid is half liquid and half gas. It means its macroscopic properties can show a combination of behaviors that we typically associate with each phase. For example, it can have gas-like diffusivity or ability to penetrate porous materials, and at the same time it can have liquid-like density and solvent strength under certain conditions. But the key message is, it is a single phase with continuously tunable properties, controlled by pressure and temperature relative to the critical point. Now, look at the orange box at the bottom of the left panel. It gives a visual clue near the critical point, critical opalescence, described as milky scattering. This is a classic experimental phenomenon. I want you to treat it as a physical indicator that the system is becoming extremely sensitive and that density fluctuations become large near the critical point. You do not need to memorize the detailed theory of scattering today, but you must remember the conceptual meaning. Near the critical point, the fluid can appear cloudy or milky because it strongly scatters light. That is a visible sign that something special is happening in the fluid structure. Now, move to the right panel, which shows an experiment photo using ethane. This is very valuable, because it turns the abstract idea of indistinguishable phases into something you can literally see. The slide shows 3 images in sequence, and at the bottom it labels them clearly. Image 1 is subcritical, meaning 2 phases, image 2 is critical opalescence, image 3 is supercritical. Let us interpret each image. In image 1, subcritical, you can see a clear phase boundary in the cell, a meniscus or interface separating a denser phase and a less dense phase. That is the liquid-vapor coexistence region, where 2 phases are present at equilibrium. The existence of a stable interface tells you immediately, the phases are distinct, and the system is below the critical point in terms of conditions. In image 2, near the critical point, you see the fluid becoming cloudy or milky. This corresponds to critical opalescence. The interface becomes less clear, and the system looks like it is filled with scattering. This indicates that density fluctuations are becoming very strong, and the system is approaching the condition where the distinction between liquid and vapor disappears. In image 3, supercritical, the cloudiness disappears, and there is no visible interface. The cell looks uniform again. This is the important point. Above the critical point, the system is single phase. It is not 2 phases mixed together. It is 1 phase, and therefore no meniscus exists. Now, I want you to connect these visuals back to the 2 diagrams we already discussed. On the P-T diagram, the critical point is the end of the liquid-vapor boundary line. The photo demonstrates what end of the boundary means physically. The meniscus disappears. On the P-V isotherm diagram, below T sub C you have a plateau indicating 2-phase coexistence. At T sub C the plateau collapses to a point, and above T sub C there is no plateau. The photo demonstrates the same transition, 2 phases, then a special critical region with opalescence, then a single uniform supercritical phase. Now let us do a checkpoint. I want you to answer these questions mentally, because they are exactly the kind of reasoning that shows true understanding. First, if someone asks, what is the critical point, can you answer without using only the words end of boundary? You should be able to say, it is the condition where liquid and vapor become indistinguishable, their densities converge, and the interface disappears, so the liquid-vapor coexistence curve terminates. Second, if someone asks, why can you not liquefy above T sub C by pressure alone, Can you answer using the phase diagram logic? You should be able to say, because above T sub C there is no liquid, vapor boundary line to cross, the system remains single phase, so compression changes density continuously without forming a separate liquid phase. Third, if someone asks, what does critical opalescence indicate, you should be able to say, it is a visible sign near the critical point where the fluid strongly scatters light and appears milky, indicating unusually large fluctuations in the fluid near the critical condition. Let me summarize this slide. At the critical point, liquid and vapor become indistinguishable, and the liquid-vapor boundary ends, meaning there is no surface separating phases. Above T sub C, increasing pressure alone cannot liquefy the fluid, and the fluid exists as a single supercritical phase with properties that can be intermediate between gas-like and liquid-like. Near the critical point, critical opalescence can appear as a milky scattering, and the ethane experiment photos illustrate the transition from two phases, to critical opalescence, to a uniform supercritical state. Now we transition to the next slide. Next, we will formalize the critical properties as critical constants, specifically T sub C, P sub C, and V sub C, and we will begin to treat them as quantitative reference values that allow us to compare substances and later construct reduced variables and real gas correction frameworks. Now we proceed to slide 9, titled Critical Properties, T sub C, P sub C, V sub C. This slide is where we turn the physical meaning of the critical point into precise, usable definitions. On the previous slide, you saw that at the critical point liquid and vapor become indistinguishable, the interface disappears, and above T sub C you cannot liquefy a gas by pressure alone. Now the question becomes, how do we capture that critical condition using measurable constants that we can place in calculations and models? The answer is exactly what this slide provides: critical temperature, critical pressure, and critical molar volume. By the end of this slide, you should be able to do two things. First, you should be able to define T sub C, P sub C, and V sub C clearly and correctly, without mixing them up. Second, you should be able to explain why these critical constants matter, especially for reduced properties and for the use of Z-charts later. Let us begin on the left panel under definitions. The first definition is critical temperature, T sub C. The slide states, critical temperature is the highest temperature where liquid-vapor coexistence is possible. I want you to pause and interpret that carefully, because it carries a deep meaning. Highest temperature where liquid-vapor coexistence is possible means, if the temperature is above T sub C, there is no pressure at which you can have a stable equilibrium between a distinct liquid phase and a distinct vapor phase. So, T sub C is a limit on the existence of a liquid-vapor phase boundary. It is not merely the temperature at the critical point. It is the temperature threshold that separates phase boundary exists from phase boundary does not exist. Now, the second definition is critical pressure, P sub C. The slide states, critical pressure is the pressure at the critical point. This sounds simple, but let us state it more carefully. At the critical point, the system has a specific pressure value associated with that unique state where liquid and vapor become indistinguishable. That pressure is P sub C. In other words, P sub C is not the pressure needed to liquefy a gas at any temperature. It is the pressure coordinate of the critical point itself, corresponding to T sub C and V sub C. Now, the third definition is critical molar volume, V sub C. The slide states, critical molar volume is the molar volume at the critical point. Here, you must remember that molar volume, V sub m, is volume per mole. So V sub C is the value of molar volume when the system is at the critical point. In the P-V isotherm picture from earlier, it is the volume coordinate of the critical point on the critical isotherm. Now read the next line, why they matter. The slide states, T sub C and P sub C set the scales for reduced properties, T sub R and P sub R, and for Z charts. This is where critical properties become powerful. Instead of treating each substance as completely unique, we use critical constants as scaling parameters. When you scale temperature by T sub C and pressure by P sub C, you create reduced variables that let you compare different substances on a common dimensionless framework. That is the logic behind corresponding states, and it is the logic behind generalized compressibility charts. Now let us move to the right panel, which gives example critical constants, selected fluids. Here you see a small table with three fluids, CO2, N2, and H2O. The columns are T sub C in Kelvin, P sub C in bar, and V sub C in liter per mole. Let us read the first row. For CO2, the slide shows T sub C equals 304.18 Kelvin, P sub C equals 73.80 bar, and V sub C equals 0.0919 liter per mole. This is a useful reference because we already saw CO2 in the Andrews isotherms example, and now you see how its critical temperature and critical pressure appear numerically as constants. Now the second row. For N2, the slide shows T sub C equals 126.19 Kelvin, P sub C equals 33.978 bar, and V sub C approximately equals 0.0894 liter per mole, with an asterisk. The asterisk indicates that V sub C is estimated, and the note at the bottom explains how. Now the third row. For H2O, the slide shows T sub C equals 647, noted as average, Kelvin, P sub C equals 220.64 bar, and V sub C approximately equals 0.0559 liter per mole, again with an asterisk. Now, do not rush past the units, because units matter a lot here. T sub C is in Kelvin, not in degrees Celsius. P sub C is in bar. V sub C is in liter per mole. If you later use these numbers in calculations, you must be consistent with R and with your pressure and volume units. But for now, the main learning point is conceptual comparison. Water has a much higher critical temperature and critical pressure than nitrogen, which tells you water's intermolecular interactions are stronger and it requires much higher conditions to reach critical behavior. CO2 sits in between in these examples. Now, look at the small note below the table. It says V sub C is estimated from V sub C equals 1 over rho sub C using NIST critical densities. This note is telling you that critical volume can be obtained from critical density, because density is mass per volume, and molar volume is related to molar mass divided by density. The key point is simply that V sub C is not always tabulated directly in the same way as T sub C and P sub C, but it can be inferred from critical density data. Now, look at the blue statement at the bottom of the right panel. It says, use T sub C and P sub C to build reduced variables, T sub R equals T over T sub C, and P sub R equals P over P sub C. This is a major transition point in the lecture. We are about to move from critical constants as definitions into critical constants as scaling tools. Before we transition, let us do a checkpoint. I want you to test whether your definitions are precise. First, if I ask you, what is T sub C, you should answer, it is the highest temperature at which liquid-vapor coexistence is possible. Not simply the critical temperature, but the highest temperature for two-phase equilibrium between liquid and vapor. Second, if I ask you, what is P sub C, you should answer, it is the pressure at the critical point, corresponding to T sub C and V sub C. Third, if I ask you, what is V sub C, you should answer, it is the molar volume at the critical point. Fourth, if I ask you, why do we care, you should answer, because T sub C and P sub C set scales for reduced properties, which support corresponding states thinking and generalized real gas corrections such as Z charts. Let me summarize this slide. Critical properties are defined at the critical point. T sub C is the highest temperature where liquid-vapor coexistence can occur. P sub C is the pressure at the critical point. V sub c is the molar volume at the critical point. These constants matter because they allow us to scale temperature and pressure to form reduced variables, T sub r and P sub r, which are central for generalized real gas correlations and for compressibility-based calculations. Now we transition to the next slide. Next, we will focus directly on reduced properties and corresponding states, using T sub r equals T over T sub c and P sub r equals P over P sub c. This will prepare you to use the compressibility factor Z in a systematic way across different substances and conditions. Now we proceed to slide 10, titled Reduced Properties and Corresponding States. This slide is a turning point in the lecture. Up to this point, we have been building meaning, what the critical point is, what critical constants are, and why real gases deviate from ideal behavior. Now we start building a universal strategy, how to take different substances, with different critical constants, and put them onto a common, dimensionless scale so that we can predict real gas behavior in a systematic way. By the end of this slide, you should be able to do three things. First, you should be able to define the reduced variables, T sub r, P sub r, and V sub r. Second, you should be able to interpret what those reduced numbers mean physically, especially what closeness to critical conditions means. Third, you should be able to describe the practical workflow for solving problems using corresponding states, including estimating Z and correcting the ideal gas law. Let us begin on the left side, under step-by-step, reduced variables. The slide says, we scale pressure and temperature using critical constants. That sentence is the key idea. We take a real temperature, T, and compare it to a substance's critical temperature, T sub c. We take a real pressure, P, and compare it to a substance's critical pressure, P sub c. And we take a real molar volume, V sub m, and compare it to the critical molar volume, V sub c. Now look at the three equations shown in the center left. First equation, T sub r equals T over T sub c. Please read it slowly. T sub r is reduced temperature. It is dimensionless because it is a ratio of two temperatures in the same unit. In practice, you must use absolute temperature, meaning Kelvin, for both T and T sub c, so the ratio is meaningful. Second equation, P sub r equals P over P sub c. P sub r is reduced pressure. Again, it is dimensionless. As long as P and P sub c are in the same unit, such as bar with bar, or kilopascal with kilopascal, the ratio is consistent. Third equation, V sub r equals V sub m over V sub c. V sub r is reduced molar volume. It is also dimensionless, and it tells you how the current molar volume compares with the critical molar volume. Now, I want you to understand why we do this scaling. A raw temperature value, like 300 Kelvin, means different things for different substances. For some substances, 300 Kelvin is far above their critical temperature. For other substances, 300 Kelvin might be below their critical temperature. So the raw number does not tell you how close you are to the critical region. But T sub r does. For example, if T sub r is close to 1, you are near T sub c. If T sub r is much larger than 1, you are far above the critical temperature. If T sub r is below 1, you are below the critical temperature, where liquid-vapor coexistence is possible. Now the slide provides the interpretation explicitly. It says, T sub r tells how close the temperature is to T sub c. So, when T sub r equals 1, you are at the critical temperature. When T sub r equals 2, your temperature is twice the critical temperature, meaning you are relatively far from the critical temperature in a normalized sense. When T sub r equals 0.8, you are below critical temperature, which is important for phase behavior. Then it says, P sub r tells how close the pressure is to P sub c. Again, when P sub r equals 1, you are at the critical pressure. When P sub r is much less than 1, pressure is low relative to the critical pressure. When P sub r is significantly greater than 1, pressure is high relative to the critical pressure. Now look at the section why we do this. The slide states, many fluids show similar behavior at the same T sub r and P sub r, and this is the basis of the approximate law of corresponding states. This is the core philosophy: if two different fluids are at the same reduced temperature and reduced pressure, they are in a comparable normalized thermodynamic state, and therefore they tend to have similar dimensionless properties, such as Z. I want you to take the word approximate seriously. It means this is not a perfect law for all substances under all conditions. It is a powerful engineering and physical chemistry approximation that works reasonably well for many simple fluids, and it becomes the starting point for generalized correlations. Now, move to the right panel, titled What You Will Do in Problems. This is where I want you to build a mental algorithm. The slide says, given temperature and pressure, and critical constants T sub C and P sub C, you will do the following steps. Step 1, compute T sub R and P sub R. That means you take your actual temperature in Kelvin and divide by T sub C, and you take your actual pressure in the same unit as P sub C and divide by P sub C. Step 2, use a generalized Z chart, or an equation of state, to estimate Z. This is the first time the slide explicitly connects reduced variables to Z. The idea is, the Z chart is typically organized in terms of reduced pressure and reduced temperature. So once you have T sub R and P sub R, you can locate the point on the chart and read an estimate of Z. Alternatively, you can use an equation of state to compute Z. Step 3, correct the ideal gas law using Z. That means you replace PV equals nRT with PV equals Z times N times R times T, or in molar form you use PV sub M equals ZRT. This is how corresponding states becomes a practical calculation method. Now, the blue box at the bottom gives the key assumption for two-parameter corresponding states. It says, fluids with the same T sub R and P sub R have similar Z. This is the central assumption behind generalized compressibility charts. It is also the statement that makes reduced variables meaningful. Reduced variables are not just ratios. They are coordinates in a generalized similarity map. Now I want you to do a checkpoint that is more procedural than conceptual. Imagine you are solving a problem. You are given a gas at a certain pressure and temperature, and you are asked to find the molar volume or the amount of gas in a container. Ask yourself, what is the wrong first move? The wrong first move is to immediately use PV equals nRT without checking conditions. The correct first move is to compute reduced temperature and reduced pressure, so you can judge whether real gas effects might matter and, if needed, obtain Z. Then, and only then, you write the corrected relation. Also, please note one more subtle point. On this slide, V sub R is defined as V sub M over V sub C, but in many practical Z-chart workflows, you often do not need V sub R directly at the beginning. You typically start with T sub R and P sub R to find Z, then you compute molar volume from PV sub M equals ZRT. But V sub R is still conceptually useful because it reminds you that volume can also be scaled, and it becomes important in deeper corresponding states theory and some forms of generalized correlations. Let me summarize this slide. Reduced properties are dimensionless variables obtained by scaling with critical constants, T sub R equals T over T sub C, P sub R equals P over P sub C, and V sub R equals V sub M over V sub C. T sub R and P sub R indicate how close a state is to critical conditions on a normalized scale. The approximate law of corresponding states says many fluids show similar behavior at the same T sub R and P sub R. In problems, you compute T sub R and P sub R, use a generalized Z chart or an equation of state to estimate Z, and then correct the ideal gas law using Z. Now we transition to the next slide. Next, we will focus explicitly on the compressibility factor Z itself, how it is defined, what it means physically, and how its value tells you whether attractions or repulsions are dominating under given conditions. Now we proceed to slide 11, titled Compressibility Factor, Z. This slide introduces the main quantitative tool we will use to measure and correct real gas behavior. Up to this point, we have built the physical reasons for non-ideality, and we introduced reduced properties as a way to compare different substances. Now, Z gives us a single number that captures how far a gas departs from ideal behavior under a given temperature and pressure. By the end of this slide, you should be able to do 4 things. First, you should be able to define Z correctly from the molar form of the ideal gas law. Second, you should be able to read the definition out loud in a TDS-friendly way, and understand what each symbol means. Third, you should be able to interpret Z equal to 1, Z less than 1, and Z greater than 1 in terms of molecular forces and compressibility. Fourth, you should be able to interpret the typical Z versus pressure curves shown on the right side and explain why many gases dip below 1 first and then rise above 1 at high pressure. Let us begin on the left side under definition. The slide tells you to start from the ideal gas relationship in molar form, which is written as P times V sub m equals R times T. Please notice, this is the ideal gas law, but expressed per mole. V sub m is molar volume, meaning V divided by N. So, P times V sub m equals R times T is just another way of writing PV equals nRT, but it is very convenient because it isolates the per mole behavior. Now the slide states, for a real gas, PV sub m is not equal to RT. That is the simplest way to say, ideal behavior fails. So, instead of abandoning the structure, we define a correction factor. The slide defines Z as Z equals P times V sub m divided by R times T. Let me say it clearly in spoken form, Z equals P times V sub m over R times T. Now, I want you to interpret this definition as a ratio. It is a ratio of what the gas actually does to what the ideal gas model predicts. In the ideal gas model, PV sub m should equal RT. So if the gas were ideal, the ratio PV sub m over RT would be exactly 1. That is why Z equals 1 means ideal behavior. So, Z is essentially telling you, how much larger or smaller is PV sub m compared with RT. Now, the slide provides interpretation bullets. Let us go through them carefully. First, Z equals 1 implies ideal behavior. This is straightforward. Second, Z less than 1 means attractions dominate, and the gas is more compressible. I want you to be very careful with the phrase more compressible, because students can misinterpret it. More compressible here means that, compared with the ideal gas prediction, the real gas occupies a smaller molar volume at the same pressure and temperature, or equivalently, it produces a lower pressure at the same molar volume and temperature. The physical reason is attractions. If molecules attract, they pull inward, reducing the effective force on the walls, so pressure can be lower than ideal for the same V sub m and T. That makes PV sub m smaller than RT, so Z becomes less than 1. Third, Z greater than 1 means repulsions or finite size dominate, and the gas is less compressible. Again, interpret it carefully. When finite size and repulsions dominate, molecules resist being packed together. That tends to increase the pressure compared with ideal at the same V sub m and T, or tends to increase the molar volume required at a given pressure and temperature compared with ideal. In that case, PV sub m becomes larger than RT, so Z becomes greater than 1. So, already, Z is giving you a quantitative way to decide which physical effect is dominating. Attraction-dominated regimes correspond to Z below 1, and crowding or repulsion-dominated regimes correspond to Z above 1. Now move to the right side, typical behavior, Z versus P. There is a plot with Z on the vertical axis and pressure, P, in atmosphere on the horizontal axis. There is also a horizontal line labeled ideal gas, which corresponds to Z equals 1. Several gases are shown, N2, CH4, H2, O2, and CO2. The curves illustrate that Z is not constant. It changes with pressure, and the shape depends on the gas. Now, let us interpret the general pattern that the slide highlights at the bottom. The curves show attractions first, a dip, then repulsions, a rise, at high pressure. This is a powerful physical story. At moderate pressures, many gases show Z dropping below 1. That indicates that attractive forces are dominating the deviation. But as pressure increases further, the curves rise above 1. That indicates that finite size and repulsive effects dominate at high pressure because of crowding. Now, please look carefully at the CO2 curve, which is shown as the yellow curve. It dips quite strongly below 1 at relatively low to moderate pressures, and then it rises as pressure becomes very high. This is consistent with the idea that CO2 has relatively strong intermolecular attractions compared with some lighter gases, so the attraction-dominated region is more pronounced. Meanwhile, H2, shown as the orange curve, stays above 1 across much of the range. That suggests that attraction effects are weaker relative to the other effects in the shown conditions, and the deviations may be dominated by repulsion or size effects in that pressure range. The slide does not provide exact temperatures or detailed conditions for each curve, so we must not overinterpret the exact values. But the qualitative pattern is absolutely clear and safe. Many real gases can show Z less than 1 at intermediate pressures, then Z greater than 1 at high pressures. Now, I want you to connect the slide back to our earlier ideal versus real gas discussion. In the ideal versus real gas slide, we said attractions reduce measured pressure and can reduce volume at fixed pressure, while finite molecular size becomes important at high pressure. This Z plot is the numerical reflection of that story. Z below 1 corresponds to attraction-dominated behavior. Z above 1 corresponds to crowding and repulsion-dominated behavior. So, the story is consistent across slides, but now it is encoded in a single parameter. Now let us do a checkpoint. I want you to test your understanding with a short reasoning exercise. First, if Z equals 1, what does that mean physically? It means the gas behaves ideally at that condition. Second, if you compute Z and you find Z equals 0.8, what should you conclude? You should conclude that attractions dominate under those conditions, and the gas is more compressible than the ideal prediction. Third, if you compute Z and you find Z equals 1.2, what should you conclude? You should conclude that repulsions or finite molecular size dominate under those conditions, and the gas is less compressible than the ideal prediction. Fourth, if someone shows you a Z versus pressure curve that dips below 1 and then rises above 1, what story should you tell? You should say, at moderate pressure, attractions dominate and reduce Z, at high pressure, finite size and repulsions dominate and increase Z. Now, a very practical note. The definition Z equals PV sub m over RT also tells you how to use Z in calculations. If you know Z, you can write PV sub m equals ZRT. That looks almost identical to the ideal gas law, but now it includes Z. So, Z becomes the gateway to correcting ideal calculations without changing the overall structure of your equations. Let me summarize this slide. We start from the molar ideal gas law, PV sub m equals RT. For a real gas, this equality fails, so we define the compressibility factor Z as Z equals PV sub m over RT. Z equals 1 indicates ideal behavior. Z less than 1 indicates attractions dominate, making the gas more compressible than ideal. Z greater than 1 indicates repulsions and finite size dominate, making the gas less compressible than ideal. Typical Z versus pressure behavior often shows an attraction-driven dip below 1 followed by a repulsion-driven rise above 1 at high pressure. Now we transition to the next slide. Next, we will build the corrected form of the ideal gas law explicitly, moving from the definition of Z into the operational equation PV equals Z times N times R times T, and we will discuss how this correction is used in real problem-solving workflows. Now we proceed to slide 12, titled Derivation, PV equals Z nRT, YZ is a correction factor. This slide is short in appearance, but conceptually it is crucial, because it shows you exactly how Z fits into the ideal gas structure without changing the overall form of the equation. By the end of the slide, you should be able to reproduce this derivation step by step, and you should be able to explain, in words, why Z is called a correction factor. Let me connect the slide to the previous one. On the previous slide, we defined the compressibility factor Z as Z equals P times V sub m over R times T, and we interpreted Z equal to 1, Z less than 1, and Z greater than 1. That definition is already powerful, but it becomes operational only when you can turn it into an equation that you can use directly in problem solving. That is exactly what this slide does. It takes the definition of Z and rearranges it into a real gas form that mirrors the ideal gas law. Now, look at the left panel. It is titled Step by Step, and it provides 4 numbered steps. I will follow them exactly, and I want you to follow the logic, not just the algebra. Step 1, define molar volume, V sub m equals V over N. Read that carefully. V sub m is the molar volume. It is the total volume divided by the number of moles. This is simply a definition. There is no physics yet. We are only defining a convenient variable. Step 2, write the ideal gas law in molar form, P times V sub m equals R times T. This comes from the usual ideal gas law PV equals nRT by dividing both sides by n. When you divide PV equals nRT by n, you get P times V over n equals RT. And since V over n is V sub m, you get PV sub m equals RT. This is important because now the equation describes the relationship per mole. Step 3, state the key observation for real gases. The slide says, for a real gas, PV sub m differs, and therefore define Z equals PV sub m divided by RT. This is the exact definition of Z. Here is how you should think about it. If the ideal gas law were always true, PV sub m would always equal RT, so the ratio would always equal 1. But because a real gas does not satisfy that equality, we capture the deviation by defining the ratio as Z. So Z is literally the factor that tells you how much PV sub m deviates from RT. Now, step 4, rearrange. The slide says, rearrange PV sub m equals ZRT, then PV equals Z nRT. Let us do that carefully, and I want you to see every step. Start from the definition, Z equals PV sub m over RT. If you multiply both sides by RT, you get Z times R times T equals P times V sub m. Now simply swap the order on the right hand side, and you write PV sub m equals ZRT. That is the corrected molar form. It is the ideal molar form, but multiplied by Z. Now, if you want the non-molar form, you substitute V sub m equals V over N back into PV sub m equals ZRT. So you write P times V over N equals ZRT. Then multiply both sides by N, and you obtain PV equals Z nRT. Now pause here. This is the most important conceptual point of the slide. The real gas equation PV equals Z nRT has the same structure as the ideal gas law PV equals nRT. The only difference is that we multiply the right-hand side by Z. That is why Z is called a correction factor. It corrects the ideal model by scaling the ideal prediction up or down depending on whether the real gas is less ideal or more ideal under that condition. Now, I want you to interpret what correction factor means physically, not only algebraically. If Z is less than 1, the corrected right-hand side becomes smaller than nRT. That means at a given n, R, and T, the product PV is smaller than the ideal prediction. That is consistent with attraction-dominated behavior. Either pressure is lower at a given volume, or volume is lower at a given pressure, compared with ideal. If Z is greater than 1, the corrected right-hand side becomes larger than nRT. That means PV is larger than the ideal prediction, consistent with repulsion and finite size dominated behavior. So the correction factor does not only fix the math. It encodes molecular physics into the equation. Now look at the bottom of the slide, where it states, final real gas form, same structure as ideal gas law, but corrected, and then it displays the large equation PV equals Z nRT. I want you to be able to read this in a clean spoken way for TDS, P times V equals Z times N times R times T. Now, I want you to notice a subtle but important idea. This corrected form is extremely convenient because it allows you to use the same algebra you already know from ideal gas problems, but with one additional input, Z. So, in a problem, if you are asked to find volume, you can write V equals Z nRT over P. If you are asked to find pressure, you can write P equals Z nRT over V. If you are asked to find moles, you can write N equals PV over Z RT. So the structure stays familiar, but the physics is more accurate. Now let us do a checkpoint. Please test yourself with 3 quick tasks. First, can you state the definition of molar volume? You should say, V sub m equals V over N. Second, can you start from Z equals PV sub m over RT and derive PV sub m equals Z RT, without skipping steps? You should be able to multiply both sides by RT and rearrange. Third, can you substitute V sub m equals V over N and obtain PV equals Z nRT? You should be able to do it smoothly. If you can do these 3 tasks, you have mastered why Z is a correction factor and how it modifies the ideal gas law. Let me summarize this slide. We define molar volume as V sub m equals V over N. The ideal gas law in molar form is PV sub m equals RT. For a real gas, PV sub m differs from RT, so we define Z as Z equals PV sub m over RT. Rearranging gives PV sub m equals Z RT, and substituting V sub m equals V over N yields the practical real gas equation, PV equals Z nRT. Z is called a correction factor because it modifies the ideal gas structure by scaling the right-hand side to match real behavior. Now we transition to the next slide. Next, we will discuss how to obtain Z in practice, typically using generalized Z charts based on reduced pressure and reduced temperature, or by using an equation of state. That will complete the workflow. Compute T sub R and P sub R, estimate Z, and then apply PV equals Z nRT to solve real gas problems. Now we proceed to slide 13, titled Using Z in Calculations, Workflow plus Z Chart. This slide is where everything we have built so far becomes a practical problem-solving procedure. Up to this point, you have learned what critical constants mean, how to build reduced variables, and how Z corrects the ideal gas law. Now, this slide tells you exactly how to use those ideas in real calculations, and it shows you a generalized Z chart as a tool for estimating Z. By the end of this slide, you should be able to do 3 things. First, you should be able to state the workflow for real gas calculations, step by step, without guessing. Second, you should be able to explain what a generalized Z chart represents and how to read it conceptually. Third, you should be able to write the corrected volume expression, either as total volume V or molar volume V sub m, in a consistent, TDS-friendly way. Let us begin on the left panel, titled Practical Workflow. The slide starts with the given information, given temperature, pressure, and critical constants, T sub C and P sub C. This is the typical real gas problem setup. You are given a state, defined by T and P, and you are given, or you look up, the critical constants of the substance. Now the slide gives step 1, compute reduced variables. It states, T sub R equals T over T sub C, and P sub R equals P over P sub C. I want you to treat this as a mandatory step, not optional. Why? Because reduced variables are the bridge between your actual state and generalized correlations. Also, it forces you to normalize the state relative to critical conditions, which immediately tells you how close you are to regions where non-ideality becomes strong. Here is an important operational note: temperature must be in Kelvin when you compute T sub R, because reduced temperature is a ratio of absolute temperatures. Pressure just needs consistent units for P and P sub C, such as bar with bar or kilopascal with kilopascal. Now step 2, read or estimate Z. The slide provides two options. Option 1 is to use a generalized Z chart, which depends on T sub R and P sub R. Option 2 is to use an equation of state, an EOS. The important message is this: Z is not usually given directly. You either estimate it from generalized correlations or you compute it from a model equation of state. Later in the lecture, when we discuss virial and van der Waals, you will see how equations of state can predict Z. But at this stage, the Z chart is the most direct and practical tool. Now step 3, correct the ideal gas law. The slide writes the corrected volume form as V equals Z nRT over P, and it also provides the molar form as V sub m equals Z RT over P. I want you to pay attention to the structure. This is exactly the ideal gas expression for volume, but multiplied by Z. So, if you know Z, you can compute volume. If you are instead solving for pressure, you would rearrange accordingly, always keeping Z in the correct location. Now, the slide also displays, at the bottom left, the molar volume equation in large form, V sub m equals Z RT over P. Please practice reading it out loud: V sub m equals Z times R times T divided by P. In many engineering contexts, this is one of the most useful working equations for real gases when Z is available. Now, let us move to the right panel, generalized Z chart, example. This is a classic type of plot. The vertical axis is the compressibility factor, Z, labeled also as Z equals PV over RT in the chart. The horizontal axis is reduced pressure, P sub R. And the chart contains multiple curves labeled by reduced temperature, T sub R, such as T sub R equals 1.0, 1.1, 1.2, 1.3, 1.5, and 2.0. The note at the bottom says, use T sub R curves, read Z at your P sub R. This is the reading instruction. Now I will teach you how to read this chart in a systematic way, even if you cannot read every small tick label perfectly. First, identify your reduced temperature, T sub R. That tells you which curve family you should use. For example, if your T sub R is close to 1.2, you follow the curve labeled T sub R equals 1.2. If your T sub R is between two labeled curves, you conceptually interpolate between them. The slide does not specify interpolation rules, so we keep it conceptual here. You choose the curve closest to your T sub R. Second, identify your reduced pressure, P sub R. That is your x-axis coordinate. You locate that value along the horizontal axis. Third, move vertically from that P sub R value up to your chosen T sub R curve. The y-axis value at the intersection gives you Z. Fourth, once you have Z, you move back to the left panel workflow and apply V equals Z nRT over P, or V sub m equals Z RT over P, depending on what the problem asks. Now, I want you to interpret the shape of these curves, because this is where physics shows up in the chart. Notice that for T sub R close to 1, meaning near the critical temperature, the curves can show strong deviation, including a pronounced dip to lower Z values. That matches our earlier discussion: near critical conditions, real fluid behavior becomes very non-ideal. As T sub R increases, meaning you are farther above the critical temperature, the curves tend to stay closer to Z equals 1 over a wider pressure range. This matches the intuition that at higher temperature, gases behave more ideally. Also notice that as P sub R increases, Z eventually tends to rise in many curves. That corresponds to repulsions and finite size effects dominating at high density. Again, you are seeing the same physics we discussed earlier, but now expressed in dimensionless form. Now let us do a checkpoint, and I want you to imagine a concrete problem workflow, even without numbers. Suppose you are given a gas at a known temperature and pressure, and you are asked to estimate its molar volume. What should you do? First, you compute T sub R equals T over T sub C, and P sub R equals P over P sub C. Second, you use the generalized Z chart to estimate Z using your T sub R and P sub R. Third, you compute V sub M equals Z RT over P. This is your algorithm. It is not a guess. It is the structured method the slide is teaching. Now, I also want you to notice what this workflow implies about knowledge organization. To use this method, you need critical constants. That is why we spent time defining T sub C and P sub C. You also need a reliable estimate of Z, either from charts or from an EOS. That is why we will later study equations of state. They provide a predictive way to compute Z, especially when generalized charts are not sufficient or when higher accuracy is needed. Let me summarize this slide. The practical workflow for using Z in calculations is: compute reduced variables, T sub R equals T over T sub C and P sub R equals P over P sub C, estimate Z using a generalized Z chart based on T sub R and P sub R, or using an equation of state, and then correct the ideal gas law using Z, so that V equals Z n RT over P, or in molar form, V sub M equals Z RT over P. The generalized Z chart is read by selecting the appropriate T sub R curve and reading Z at your reduced pressure P sub R. Now we transition to the next slide. Next, we will move from the Z chart workflow into a more theoretical representation of non-ideality, starting with the virial equation of state, which expresses Z as a series and connects Z to molecular interactions in a structured way. Now we proceed to slide 14, titled Virial Equation of State, EOS. This slide marks an important shift in our lecture. Up to now, Z has been treated mainly as something you read from a chart or estimate from corresponding states. Now we move one step deeper. We ask, can we represent Z in a systematic mathematical form that connects directly to molecular interactions? The virial equation of state is one of the clearest answers to that question, especially at low density. By the end of this slide, you should be able to do three things. First, you should be able to explain how we go from the definition of Z to a series expansion in 1 over V sub M. Second, you should be able to interpret the physical meaning of the coefficients B of t, C of t, and D of t in an intuitive way. Third, you should be able to state the assumptions under which the virial equation works best, and what truncation means in practice. Let us start from the top of the slide, under from Z to a series expansion. The slide shows the starting point, Z equals P times V sub M over R times T. This is our definition, and it is our bridge. The key idea is that at sufficiently low density, meaning large molar volume V sub M, experiments show that Z can be represented as a power series in 1 over V sub M. Now pause. I want you to build intuition for why 1 over V sub M is the natural variable. If V sub M is large, the gas is dilute. That means molecules are far apart, so interactions are relatively weak and rare compared with the ideal gas picture. In that situation, deviations from ideality are small, and it becomes mathematically reasonable to represent those small deviations as an expansion in a small parameter. 1 over V sub M becomes small when V sub M is large. So, 1 over V sub M acts like a small expansion parameter. That is the physical reason this series makes sense at low density. Now look at the virial expansion shown on the slide. Z equals 1 plus B of t over V sub M plus C of t over V sub M squared plus D of t over V sub M cubed, and so on. Let me read it in a TDS-friendly way. Z equals 1 plus B of t divided by V sub M, plus C of t divided by V sub M squared, plus D of t divided by V sub M cubed, plus ... Now, interpret the structure. The first term is 1. That corresponds to ideal behavior. If the gas were ideal, Z would be exactly 1. The remaining terms represent corrections to ideality. Each correction term becomes smaller as V sub m becomes larger, because you are dividing by V sub m, or V sub m squared, or V sub m cubed. So in the dilute limit, the correction terms vanish, and Z approaches 1. That matches the physical expectation that gases become more ideal at low density. Now, the slide provides physical meaning, easy interpretation. This is the part I want you to internalize. It states, B of T is a two-body, or pair, interaction correction. C of T is a three-body interaction correction. And higher terms matter only when the gas becomes denser. Let us unpack that carefully. B of T depends on temperature, and it captures the leading correction due to interactions between pairs of molecules. At low density, most molecules are far apart, and the most common interaction events involve only two molecules at a time. So the first correction to ideality naturally comes from pair interactions. That is why B of T is called the second virial coefficient, and it represents the two-body contribution. C of T is the next correction. It represents three-body interactions. At low density, the probability that three molecules are close enough simultaneously to have a correlated interaction is much smaller than the probability of pair interactions. That is why the three-body contribution is a higher-order term, divided by V sub m squared. It becomes relevant only when density increases. D of T and higher coefficients represent even more complex multi-body interaction contributions. These become significant only when the gas becomes much denser, because then many molecules are close enough for multi-body effects to matter. So, the virial series is not just mathematics. It is a hierarchy of physical interaction complexity, two-body effects first, then three-body, then higher-body contributions. Now, the slide provides assumptions, when it works best. It says, single phase, no condensation, low to moderate pressure. And it says, truncation is acceptable, for example keep only B of T over V sub m. Let us interpret this carefully. First, single phase, no condensation. Why is that required? Because near condensation, the gas is no longer a small perturbation of the ideal gas. Density becomes high, interactions become dominant, and the system can enter a two-phase region where the concept of a single uniform molar volume becomes complicated. In that region, representing Z as a smooth series in 1 over V sub m may fail or become inaccurate. So, the virial equation is primarily a gas phase, single-phase representation. Second, low to moderate pressure. This is consistent with low density. Low pressure tends to correspond to large molar volume, meaning 1 over V sub m is small. That is exactly the regime where the expansion converges well. Now, truncation. Truncation means you stop the infinite series after a finite number of terms. For example, the simplest truncation is Z approximately equals 1 plus B of T divided by V sub m. This is a first-order correction beyond ideality. It includes only pair interactions. The slide is telling you that this can be acceptable in appropriate regimes, especially when the gas is not too dense. Now, I want you to connect virial thinking to our earlier Z versus pressure plot. The virial expansion is a way to represent the same Z behavior, but now as a function of molar volume and temperature through coefficients. It helps explain why Z deviates from 1, and it also creates a model that can be fitted to experimental data. Also, connected to the workflow slide. Previously, we said you can estimate Z using a Z chart or an equation of state. Virial is an example of an equation of state approach. It gives you a formula to compute Z, provided you know the coefficients B of T, C of T, and so on. Now let us do a checkpoint. I want you to test your understanding with 3 conceptual questions. First, Why is 1 over V sub m a natural expansion variable? You should answer, because at low density V sub m is large, so 1 over V sub m is small, and deviations from ideality can be treated as small corrections. Second, what is the meaning of B of t and C of t? You should answer, B of t represents two body or pair interaction corrections, and C of t represents three body interaction corrections. Third, when is truncation acceptable? You should answer, in single-phase gas conditions at low to moderate pressure, where the gas is not too dense, and higher-order interaction terms are small. Let me summarize this slide. Starting from Z equals PV sub m over RT, experiments show that at sufficiently low density Z can be represented as a power series in 1 over V sub m, Z equals 1 plus B of t over V sub m plus C of t over V sub m squared plus D of t over V sub m cubed, and so on. B of t captures two body interaction corrections, C of t captures three body corrections, and higher terms matter mainly at higher density. The virial approach works best in single-phase conditions without condensation at low to moderate pressure, and truncation, such as keeping only the B of t term, can be acceptable in that regime. Now we transition to the next slide. Next, we will discuss how the virial equation can be written in practical forms, what truncations look like in calculations, and how these forms connect to real gas correction workflows in engineering problems. Now we proceed to slide 15, titled Virial EOS, Practical Forms, and What You Assume. This slide is important because it teaches you a professional habit. Whenever you use an approximation, you must be able to state what you assumed, and you must know when that assumption is reasonable. The virial equation of state is powerful, but it is not magic. It is a controlled approximation, and this slide shows you two practical truncated forms and the meaning of each truncation. By the end of this slide, you should be able to do three things. First, you should be able to explain what truncation means for the virial series and why truncation is used. Second, you should be able to interpret the first practical form, Z approximately equals 1 plus B of t over V sub m, including the assumption behind it. Third, you should be able to interpret the pressure series form, Z equals 1 plus B prime of t times P plus C prime of t times P squared plus ... and understand why it is useful at low pressure. Let us start with the left panel, titled Truncation Number 1, Molar Volume Form. The slide says, keep only the first correction term, and it shows Z approximately equals 1 plus B of t divided by V sub m. Please read it out loud in a clear spoken form. Z is approximately equal to 1 plus B of t over V sub m. Now, what does this mean? It means we take the full virial series. Z equals 1 plus B of t over V sub m plus C of t over V sub m squared plus D of t over V sub m cubed, and so on. And we stop after the first correction term. We ignore the C of t term, the D of t term, and higher terms. This is what truncation means. It means we replace an infinite series with a finite approximation that keeps only the most important terms in the regime of interest. Now, why is the B of t term the first and why is it often the most important? Because B of t represents two body interactions, which dominate at low density. When the gas is dilute, it is much more likely that the main deviation from ideality comes from pair interactions rather than complex three-body or multi-body correlations. Now, the slide explicitly states the assumption under this truncation. It says, the gas is dilute enough that three-body and higher interactions are negligible. That is exactly the physical statement behind dropping C of t and higher terms. You are assuming that the probability of three molecules interacting in a correlated way is small enough to ignore, so the pair interaction correction is sufficient. Now I want you to connect this to the controlled approximation idea. This is controlled because we know the hierarchy of terms, B over V sub m scales as 1 over V sub m, C over V sub m squared scales as 1 over V sub m squared, and so on. At large V sub m, 1 over V sub m is small, and 1 over V sub m squared is even smaller. So you have a built-in mathematical reason why the first correction term dominates in the dilute limit. This is what makes it a controlled expansion. Now move to the right panel, titled Truncation Number 2, Pressure Series. The slide says, sometimes Z is expanded in powers of pressure, useful at low pressure. And it shows Z equals 1 plus B prime of T times P plus C prime of T times P squared, plus ... Let me read it in a TDS-friendly way. Z equals 1 plus B prime of T times P, plus C prime of T times P squared, plus ... Now, conceptually, what is happening here? Instead of expanding Z in terms of 1 over V sub m, we expand Z in terms of pressure. This can be useful because in many experiments and many engineering problems, pressure is the directly controlled or measured variable. At sufficiently low pressure, pressure is small, so expanding in powers of P becomes another way to build a controlled approximation. However, I want you to be careful. This form does not mean pressure is always the best variable. It means there are regimes where pressure series expansions are convenient and accurate, especially at low P. The slide is teaching you that virial thinking is flexible. You can represent non-ideality as a series in density-related variables like 1 over V sub m, or as a series in pressure, depending on what is convenient and what regime you are in. Now look at the key message for students' bullets on the right panel, because they are essentially the philosophy of this slide. First bullet, the virial EOS is a controlled approximation. That means you are not guessing a random correction. You are using a systematic expansion whose terms have physical meaning and whose accuracy improves in the appropriate limit. Second bullet, validity depends on density or pressure range and proximity to phase change. This is the professional warning label. If the gas becomes dense, or if you approach condensation and phase boundaries, higher order interactions become important, and the truncated virial form may fail. So you must always evaluate whether the state is in a regime where truncation is justified. Now, I want you to build a habit. When you see a truncated expression like Z approximately equals 1 plus B of T over V sub m, do not only ask, can I use this formula? You must ask, what assumption is encoded here? The assumption is, the gas is dilute enough that three-body and higher interactions are negligible, and the system is single-phase and not near condensation. Also, notice that both practical forms share a common anchor, Z equals 1 plus corrections. The one is ideal behavior. The correction terms are systematic deviations from ideality. Now let us do a checkpoint. I want you to answer these questions mentally. First, what does truncation mean in the virial context? It means keeping only the first few terms of the virial series and neglecting higher order terms. Second, what assumption is made when you use Z approximately equals 1 plus B of T over V sub m? You assume the gas is dilute enough that three-body and higher interactions are negligible. Third, when might a pressure series expansion be useful? It can be useful at low pressure, where expanding Z in powers of P provides a convenient approximation. Fourth, what determines whether the virial approximation is valid? The density or pressure range and how close you are to phase change, meaning whether you remain in a single gas phase far from condensation. Let me summarize this slide. The virial equation of state is used in practical truncated forms. One common truncation in molar volume form is Z approximately equals 1 plus B of T over V sub m, which assumes the gas is dilute enough that three-body and higher interactions are negligible. Another practical representation is a pressure series, Z equals 1 plus B prime of T times P plus C prime of T times P squared, and so on, which can be useful at low pressure. The key message is that virial EOS is a controlled approximation, and its validity depends on the density or pressure range and proximity to phase change. Now we transition to the next slide. Next, we will move from the virial framework to a classic physically motivated equation of state, the van der Waals equation, where we explicitly introduce two parameters, A and B, to represent attractions and finite molecular size in a single compact formula. Now we proceed to slide 16, titled Van der Waals equation of state, EOS. This slide introduces one of the most famous real gas equations of state, and more importantly, it shows you a very clear philosophy. Instead of treating non-ideality as a purely empirical correction, we can try to improve the ideal gas law using physical corrections that directly reflect what is wrong in the ideal model. By the end of this slide, you should be able to do three things. First, you should be able to state the two physical problems in the ideal gas model that van der Waals tries to fix. Second, you should be able to interpret the meaning of the van der Waals parameters A and B in physical terms. Third, you should be able to explain why, when volume is large and pressure is low, the van der Waals equation reduces back toward ideal gas behavior. Let us start with the left panel, which states the goal very clearly: improve PV equals nRT using physical corrections. This is a key theme. In the virial approach, we built a series expansion based on interaction hierarchy and low-density behavior. In the van der Waals approach, we build a compact equation by correcting the two ideal gas assumptions that fail most clearly. Now, the slide lists two physical problems in the ideal gas model. It labels them as A and B. Problem A, finite molecular size, which implies less free volume for motion. I want you to visualize this carefully. In the ideal gas law, the volume V is treated as fully available space for molecules to move in. But in reality, molecules occupy space. So, the free volume available for molecular translation is smaller than V. Van der Waals accounts for this by introducing a volume correction. Conceptually, you replace V by an effective volume, V minus something. That something is related to the excluded volume due to finite molecular size. Problem B, attractions reduce the measured pressure, described here as weaker wall impacts. This connects directly to our earlier slide on ideal versus real gases. In a real gas with attractions, molecules approaching the wall are pulled back slightly by neighboring molecules. That reduces the momentum transfer to the wall compared with the ideal case, which means the measured pressure can be lower than the ideal gas prediction at the same V and T. Van der Waals accounts for this by introducing a pressure correction. Conceptually, you do not use the measured pressure P directly in the ideal gas structure. Instead, you use an effective pressure that is higher than the measured pressure, because the measured pressure has been reduced by attractions. Then the slide concludes, Van der Waals adds one correction to V and one correction to P. That sentence is the essence of the model. One correction targets excluded volume, one correction targets attractions. Now move to the right panel, which is labeled as an OpenStax figure explaining the meaning of A and B. The figure shows the transformation from the ideal gas law to the Van der Waals form. It starts with PV equals nRT. Then it shows open parenthesis P plus A n squared over V squared close parenthesis, times open parenthesis V minus NB close parenthesis, equals nRT. I want you to practice reading this clearly. The Van der Waals equation in this form is P plus A n squared over V squared, times V minus NB, equals nRT. Now, interpret the structure. The volume correction is V minus NB. That means the effective volume available for motion is smaller than the container volume by an amount proportional to the number of moles. The parameter B represents excluded volume per mole. So B is connected to molecular size. If B is larger, it means each mole of molecules excludes more volume, which is consistent with larger molecules or stronger excluded volume effects. The pressure correction is P plus A n squared over V squared. The idea is that the measured pressure P is reduced by attractions, so the ideal like pressure that would correspond to molecular motion alone would be higher. Van der Waals uses P plus AN squared over V squared as the corrected pressure that enters the ideal-like structure. The parameter A represents attraction strength. If A is larger, attractions are stronger, and the correction term AN squared over V squared becomes more significant at higher density, meaning when N over V is large. Now look at the text under the equation. It states, A is attraction strength, and B is excluded volume per mole. That is exactly the physical meaning you must remember. Now, the slide also provides an important limiting statement: when V is large, meaning low pressure, both corrections become small, so ideal behavior returns. Let us check that logically, because this is a very good habit. If V is large, then NB is usually small compared with V, so V minus NB is close to V. That makes the volume correction negligible. Also, if V is large, then N squared over V squared is very small, so the attraction correction term AN squared over V squared becomes very small. That makes P plus AN squared over V squared approximately equal to P. So the pressure correction is negligible. Therefore, in the limit of large volume, the van der Waals equation approaches the ideal gas law. This is exactly what we want from any real gas model. It should reduce to ideal behavior in the dilute limit. Now, I want you to connect this to Z conceptually. Van der Waals is another way of producing Z not equal to 1, because it modifies the relation between P, V, N, and T. In later slides, we will see how to derive critical constants from the van der Waals equation, which is a major reason this equation is historically important. It is not only a correction. It also predicts a critical point, which the ideal gas law cannot do. Now let us do a checkpoint. Please test yourself with these points. First, what are the two physical problems in the ideal gas model? You should answer, finite molecular size and intermolecular attractions. Second, what does parameter B represent? You should answer, excluded volume per mole, related to finite molecular size. Third, what does parameter A represent? You should answer, attraction strength, related to intermolecular forces. Fourth, why does van der Waals reduce to ideal behavior at large V? You should answer, because both correction terms become small when V is large, so the equation approaches PV equals nRT. Let me summarize this slide. Van der Waals improves the ideal gas law by addressing two physical failures of the ideal model: finite molecular size, which reduces free volume, and attractions, which reduce measured pressure. The van der Waals equation introduces a volume correction V minus NB and a pressure correction P plus AN squared over V squared, where A represents attraction strength and B represents excluded volume per mole. When volume is large, both corrections become small, and ideal gas behavior returns. Now we transition to the next slide. Next, we will derive the van der Waals equation more explicitly from these physical correction ideas, step by step, so you understand not only the final form, but also why each correction appears exactly where it does. Now we proceed to slide 17, titled Derivation, where van der Waals EOS comes from. This is a derivation slide, and I want you to treat it as a model for how to reason in physical chemistry. You start from a simple model, you identify the physical failures, you propose controlled corrections with clear assumptions, and then you build a new equation. By the end of the slide, you should be able to reconstruct the van der Waals equation step by step, and you should be able to state the assumptions behind each correction. Let me connect the slide to the previous one. Previously, we introduced the van der Waals equation as an improvement to PV equals nRT using two physical corrections, a volume correction for finite molecular size and a pressure correction for attractions. Now we will see exactly how those corrections are written mathematically and why they have the forms shown. The slide is organized as step-by-step construction with assumptions, and it has two main parts: A, volume correction, and B, pressure correction. Let us follow that structure carefully. Part A is volume correction, finite size. The slide begins with an assumption: assume each mole excludes a volume B from molecular centers. This is a very important wording. It does not say each mole has volume B. It says each mole excludes volume B from the space where molecular centers can move. This excluded volume idea is the physical translation of finite molecular size. If molecules occupy space, their centers cannot approach arbitrarily close, and therefore some part of the container volume is not accessible for translation of molecular centers. From that assumption, the slide states, the free volume becomes V free equals V minus NB. Read that carefully in spoken form, V free equals V minus N times B. The term NB means the excluded volume scales with the number of moles. More moles means more molecular centers, more crowding, and therefore less free volume. Then the slide says, replace V by V minus NB in the ideal gas law. This is the key modeling move. The ideal gas law assumes the entire volume V is available for motion. Van der Waals says, no, the effective volume is smaller, so substitute V minus NB wherever the ideal gas law uses V. The slide then shows the result in an explicit rearranged form. P equals nRT divided by V minus NB. Let me read it, P equals N times R times T over V minus NB. This is the ideal gas law with a volume correction only. At this stage, we have not corrected pressure for attractions. We have only corrected the effective volume for finite molecular size. Now, stop and interpret physically. If V is large compared with NB, then V minus NB is close to V, and the correction is small. But if V becomes comparable to NB, the denominator shrinks, and pressure becomes much larger than the ideal prediction. That matches the crowding intuition. At high density, finite size matters strongly. Now move to part B, pressure correction, attractions. The slide begins with the next assumption: assume attractions reduce the measured pressure by an amount proportional to number density squared. Now, I want you to unpack this carefully, because it can sound mysterious if you do not connect it to physical reasoning. First, the slide states, number density is proportional to N over V. That makes sense. The number of moles per volume is a measure of how many molecules are present per unit volume. Second, it states, pressure drop is proportional to N over V squared, meaning proportional to the square of number density. Why squared? The simplest physical intuition is that attractive interactions involve pairs of molecules. The number of possible interacting pairs in a given volume increases roughly with the square of the number density. So, as density increases, the cumulative effect of attractions grows faster than linearly. Now the slide writes the pressure relationship as P real equals P ideal minus A times N over V squared. Let me read it carefully in spoken form, P real equals P ideal minus A times open parenthesis N over V close parenthesis squared. So, attractions reduce measured pressure relative to an ideal like pressure. The parameter assets how strong that pressure reduction is for a given density. Now, at this point, we have two separate corrections, a corrected volume in the ideal gas structure, and a pressure reduction due to attractions. The final step is to combine both corrections into one equation. The slide shows the combined form. Open parenthesis P plus A times N over V squared close parenthesis, times open parenthesis V minus NB close parenthesis, equals nRT. Read it clearly, open parenthesis P plus A times open parenthesis N over V close parenthesis squared close parenthesis, times open parenthesis V minus NB close parenthesis, equals N times R times T. Now, notice what happened. In the pressure correction we wrote P real equals P ideal minus A times N over V squared. If you rearrange that, you can write P ideal equals P real plus A times N over V squared. The van der Waals equation essentially uses the corrected pressure, P plus A times N over V squared, inside the ideal-like structure, because that is the pressure that would exist without the pressure reduction due to attractions. and it uses the corrected volume, V minus NB, as the effective volume available for motion. Then it sets the product equal to nRT. Now, I want you to appreciate the modeling logic. We did not derive this from first principles of statistical mechanics on this slide. We constructed it using physically motivated corrections and simplified proportionality assumptions. So, van der Waals is a semi-empirical physical model. It contains physical reasoning, but it is still approximate. That is why it works well in some regimes and not perfectly in all regimes. Now let us do a checkpoint, and I want you to reproduce the logic without looking. First, what is the free volume in the volume correction step? You should answer, V free equals V minus NB. Second, how do you modify the ideal gas law using that free volume? You should answer, replace V by V minus NB, giving P equals nRT over V minus NB. Third, what is the assumed form of the attraction-driven pressure reduction? You should answer, pressure reduction is proportional to number density squared, so P real equals P ideal minus A times N over V squared. Fourth, how do you combine both corrections into one equation? You should answer, use the corrected pressure P plus A times N over V squared and the corrected volume V minus NB, giving open parenthesis P plus A times N over V squared close parenthesis times open parenthesis V minus NB close parenthesis equals nRT. If you can state these steps clearly, you understand where the van der Waals equation comes from in the sense intended by this lecture. Let me summarize this slide. The van der Waals equation is built by correcting two failures of the ideal gas model. For finite molecular size, assume each mole excludes a volume B, so the free volume is V minus NB, and replace V by V minus NB in the ideal gas law. For attractions, assume they reduce measured pressure by an amount proportional to the square of number density, giving P real equals P ideal minus A times open parenthesis N over V close parenthesis squared. Combining both corrections yields the van der Waals equation, open parenthesis P plus A times open parenthesis N over V close parenthesis squared close parenthesis times open parenthesis V minus NB close parenthesis equals nRT. Now we transition to the next slide. Next, we will move to the molar form of the van der Waals equation and prepare for critical point analysis, where we will apply critical conditions to derive predicted critical constants from the van der Waals model. Now we proceed to slide 18, titled Critical Constants from van der Waals EOS, Step 1, Conditions. This is one of the most conceptually rich moments in the lecture. Here, the van der Waals equation is not only used as a correction to the ideal gas law. It is used as a predictive model that can generate critical constants. In other words, the equation of state is being asked to reproduce the existence of a critical point mathematically. By the end of this slide, you should be able to do three things. First, you should be able to write the van der Waals equation in molar form and read it correctly. Second, you should be able to explain why the critical point corresponds to an inflection point on the critical isotherm. Third, you should be able to compute, or at least follow, the first and second derivatives of pressure with respect to molar volume at constant temperature, and understand why we set them equal to 0 at the critical point. Let us start at the top. The slide tells you, work in molar form, where V sub m equals V over n. This is a very good choice because critical constants are usually reported per mole, and because it simplifies the algebra. Now look at the molar van der Waals equation shown. P equals RT divided by V sub m minus B, minus A divided by V sub m squared. Let me read it clearly, P equals R times T over V sub m minus B, minus A over V sub m squared. Now, interpret each term. The first term, RT over V sub m minus B, is the ideal like pressure term with a volume correction B. The second term, A over V sub m squared, is the attraction correction that reduces pressure. So this molar form contains exactly the same physical corrections we discussed earlier, but now expressed in a compact way that is convenient for differentiation. Now, the slide states the key idea for critical point analysis. The critical point is an inflection point on the critical isotherm, meaning at T equals T sub C. This connects directly to what you learned from the P-V isotherm slide earlier. At T less than T sub C you have a two-phase plateau. At T greater than T sub C you have a smooth curve. At T equals T sub C, you have the special critical isotherm that has an inflection at the critical point. So, mathematically, what is an inflection point on a curve P as a function of V sub m at fixed T? It is a point where the slope is 0 and the curvature is 0 simultaneously. The slide states that explicitly, at V sub m equals V sub C and T equals T sub C, the P-V sub m curve has 0 slope and 0 curvature. Now, look at the two conditions written in derivative form. The slide shows partial P over partial V sub m, at constant T, equals 0. And partial squared P over partial V sub m squared, at constant T, equals 0. Let me read them in a TDS-friendly way. The first condition is, the partial derivative of P with respect to V sub m at constant T equals 0. The second condition is, the second partial derivative of P with respect to V sub m at constant T equals 0. Now, why do we impose these conditions? Because at the critical point on the critical isotherm, the curve is tangent to a horizontal line and it changes curvature there. The slope becomes 0, and the curvature becomes 0. That is the mathematical fingerprint of the critical point in this model. Now, the slide instructs, compute derivatives, show the steps, and it provides the results. This is very helpful because it allows you to verify your differentiation. First derivative shown on the slide. Partial P over partial V sub m equals negative RT divided by V sub m minus B squared, plus 2a divided by V sub m cubed. Read it carefully, dP dV sub m equals minus RT over V sub m minus B squared, plus 2a over V sub m cubed. Now, let us interpret each part. The derivative of RT over V sub m minus B with respect to V sub m is negative RT over V sub m minus B squared. That makes sense because 1 over x differentiates to minus 1 over x squared. The derivative of minus a over V sub m squared is plus 2a over V sub m cubed, because minus a times V sub m to the power minus 2 differentiates to plus 2a times V sub m to the power minus 3. So the algebra is consistent. Second derivative shown on the slide. Partial squared P over partial V sub m squared equals 2RT divided by V sub m minus B cubed, minus 6a divided by V sub m to the power 4. Read it, the second derivative of P with respect to V sub m at constant T equals 2RT over V sub m minus B cubed, minus 6a over V sub m to the power 4. Again, check the logic. Differentiating minus RT over V sub m minus B squared gives plus 2RT over V sub m minus B cubed. Differentiating plus 2a over V sub m cubed gives minus 6a over V sub m to the power 4. So, again, it is consistent. Now, what do we do with these derivatives? At the critical point, we set both equal to 0, and we evaluate them at T equals T sub C and V sub m equals V sub C. So, in words, we will take minus RT sub C over V sub C minus B squared, plus 2a over V sub C cubed, equals 0. And we will take 2RT sub C over V sub C minus B cubed, minus 6a over V sub C to the power 4, equals 0. These two equations become our system of conditions. In the next slide, we will solve these equations to obtain V sub C, T sub C, and then P sub C in terms of A and B. That is why this slide is labeled Step 1, Conditions. It is setting up the mathematical constraints, not finishing the solution yet. Now let us do a checkpoint. First, can you write the Moeller-van der Waals form correctly? You should be able to say, P equals RT over V sub m minus B, minus A over V sub m squared. Second, Can you state the critical point conditions in words? You should be able to say, at the critical point on the critical isotherm, the P, V sub m curve has zero slope and zero curvature, so the first and second derivatives with respect to V sub m at constant t are zero. Third, can you identify the first and second derivative expressions as given on the slide, at least conceptually? The first derivative is a competition between the volume correction term and the attraction term. The second derivative is similarly a balance of those contributions. If you can do these, you are ready for the next step, where we will solve the conditions to obtain the critical constants predicted by the van der Waals equation. Let me summarize this slide. We work in molar form, V sub m equals V over n. The van der Waals equation becomes P equals RT over V sub m minus B, minus A over V sub m squared. The critical point is an inflection point on the critical isotherm at T equals T sub C, so at V sub m equals V sub C and T equals T sub C, the P, V sub m curve has zero slope and zero curvature. Therefore, we impose the conditions, partial P over partial V sub m at constant T equals 0, and partial squared P over partial V sub m squared at constant T equals 0. The slide provides the derivative expressions that we will set to 0 in the next step to solve for critical constants. Now we transition to the next slide. Next, we will solve these derivative conditions systematically to obtain explicit expressions for V sub C, T sub C, and P sub C in terms of the van der Waals parameters A and B, and then we will discuss what those predictions mean and where the model is limited. Now we proceed to slide 19, titled Critical Constants from van der Waals EOS, Step 2, Solve. This slide is a full algebra slide, and I want you to follow it slowly and systematically. The goal here is not only to memorize the final results. The goal is to understand how the two critical point derivative conditions produce concrete predictions for V sub C, T sub C, and P sub C in terms of the van der Waals parameters A and B. By the end of this slide, you should be able to do four things. First, you should be able to write the two equations that come from setting the first and second derivatives equal to 0 at the critical point. Second, you should be able to divide the second equation by the first equation and see why that immediately gives V sub C equals 3b. Third, you should be able to substitute V sub C equals 3b back into the first equation to obtain the expression for T sub C. Fourth, you should be able to evaluate the pressure at the critical point to obtain P sub C, and then compute the predicted critical compressibility factor Z sub C. Let us start at the top. The slide says, set the derivative expressions to 0 at T equals T sub C and V sub m equals V sub C. From the previous slide, we had dP dV sub m equals minus RT over V sub m minus B squared, plus 2 over V sub m cubed. D squared P dV sub m squared equals 2 RT over V sub m minus B cubed, minus 6 over V sub m to the power 4. Setting the first derivative to 0 at the critical point leads to equation 1 on the slide. RT sub C divided by V sub C minus B squared equals 2A divided by V sub C cubed. Read it clearly, R times T sub C over V sub C minus B squared equals 2A over V sub C cubed. Setting the second derivative to 0 at the critical point leads to equation 2 on the slide. RT sub C divided by V sub C minus B cubed equals 3A divided by V sub C to the power 4. Read it, R times T sub C over V sub C minus B cubed equals 3A over V sub C to the power 4. Now, notice something important. Both equations contain RT sub C on the left, and both contain A and V sub C on the right. So, a very efficient move is to divide one equation by the other to eliminate RT sub C and also simplify the relationship between V sub C and B. This is exactly what the slide does. The slide says, divide equation 2 by equation 1. Let us do that carefully. On the left side, you divide RT sub C over V sub C minus B cubed by RT sub C over V sub C minus B squared. Because RT sub C is common, it cancels out. And when you divide 1 over V sub C minus B cubed by 1 over V sub C minus B squared, you get 1 over V sub C minus B. So the left side becomes 1 over V sub C minus B. Now, on the right side, you divide 3 over V sub C to the power 4 by 2 over V sub C cubed. The A cancels out. V sub C cubed cancels, leaving V sub C in the denominator. And the numerical coefficient becomes 3 over 2. So the right side becomes 3 over 2 V sub C. So the division gives 1 over V sub C minus B equals 3 over 2 V sub C. Now, the slide rearranges this to solve for V sub C. Multiply both sides by V sub C minus B and by 2 V sub C to clear denominators, or follow the slide's compact rearrangement. The slide shows 2 V sub C equals 3 times V sub C minus B. Now solve that. 2 V sub C equals 3 V sub C minus 3B. Move 2 V sub C to the right, or move 3 V sub C to the left. You get negative V sub C equals negative 3B. Therefore, V sub C equals 3B. This is a very elegant result. The critical molar volume predicted by van der Waals is 3 times the excluded volume parameter B. Now the slide says, substitute V sub C equals 3B into equation 1 to obtain T sub C. Let us do that carefully. Equation 1 is RT sub C over V sub C minus B squared equals 2 over V sub C cubed. Substitute V sub C equals 3B. First, V sub C minus B becomes 3B minus B, which equals 2B. So V sub C minus B squared becomes 2B squared, which is 4B squared. Second, V sub C cubed becomes 3B cubed, which is 27B cubed. So equation 1 becomes RT sub C over 4B squared equals 2 over 27B cubed. Now solve for T sub C. Multiply both sides by 4B squared. RT sub C equals 4B squared times 2 over 27B cubed. 4 times 2 is 8. B squared over B cubed becomes 1 over B. So, RT sub C equals 8 over 27B. Then divide both sides by R. T sub C equals 8 over 27 RB. The slide writes this as T sub C equals 8 divided by 27 RB. Now the slide says, finally, evaluate P at T sub C and V sub C to obtain P sub C. This means we substitute T equals T sub C and V sub M equals V sub C into the molar van der Waals equation. P equals RT over V sub M minus B, minus A over V sub M squared. So we said P sub C equals RT sub C over V sub C minus B, minus A over V sub C squared. Now substitute V sub C equals 3B and T sub C equals 8 over 27 RB. First, V sub C minus B equals 3B minus B equals 2B. So the first term becomes RT sub C over 2B. Replace T sub C by 8 over 27 RB. Then R times T sub C becomes 8 over 27B. Divide that by 2B, giving 8 over 27B times 1 over 2B equals 8 over 54B squared, which simplifies to 4 over 27B squared. Second, the attraction term is A over V sub C squared, which becomes A over 3B squared, meaning A over 9B squared. So, P sub C equals 4 over 27B squared, minus A over 9B squared. Now put them on a common denominator. A over 9B squared is equal to 3 over 27B squared. So, P sub C equals 4 over 27B squared minus 3 over 27B squared equals A over 27B squared. So the slide's result is P sub C equals A divided by 27B squared. Now, the slide also gives the predicted critical compressibility factor Z sub C. It writes Z sub c equals P sub c V sub c over RT sub c equals 3 over 8 equals 0.375. This is a famous prediction of the van der Waals model. Let us interpret it carefully. Z sub c is the value of Z at the critical point. According to the van der Waals equation, that value becomes a universal constant, 3 over 8, which is 0.375. This is striking because it suggests that all substances would have the same Z sub c if van der Waals were perfectly accurate as a universal model. Now, look at the blue warning box at the bottom. It says, important, real fluids do not all have Z sub c equals 0.375. This is a van der Waals prediction, and it is a model limitation. This statement is extremely important. It reminds you that van der Waals captures key physics in a simple way, but it is not quantitatively perfect for all real substances. Real fluids have different molecular shapes, polarity, and interaction details that are not fully captured by only two parameters A and B. So, the predicted universality of Z sub c is an approximation, not a universal truth. Now let us do a checkpoint. I want you to test yourself on the logical flow, not the memorization. First, what are the two equations you start from at the critical point? You start from the first and second derivative conditions set to 0, giving equation 1 and equation 2 on the slide. Second, what is the key trick to solve for V sub c quickly? You divide equation 2 by equation 1 to eliminate RT sub c and A, and you obtain a simple relationship that leads to V sub c equals 3b. Third, how do you get T sub c? You substitute V sub c equals 3b into equation 1 and solve for T sub c, giving T sub c equals 8 over 27 Rb. Fourth, how do you get P sub c? You substitute T sub c and V sub c into the molar van der Waals equation to get P sub c equals A over 27b squared. Fifth, what is Z sub c predicted by van der Waals? It is 3 over 8, equal to 0.375, but real fluids do not all share this value. Let me summarize this slide. By setting the first and second derivative conditions to 0 at the critical point, we obtain two equations relating T sub c, V sub c, A, and B. Dividing the second equation by the first yields V sub c equals 3b. Substituting V sub c equals 3b into the first equation gives T sub c equals 8 over 27 Rb. Evaluating the van der Waals pressure at T sub c and V sub c gives P sub c equals A over 27b squared. The model predicts a universal critical compressibility factor Z sub c equals 3 over 8, which is 0.375, but real fluids do not all have this value, highlighting a limitation of the van der Waals model. Now we transition to the next slide. Next, we will discuss why more sophisticated equations of state were developed beyond van der Waals, and how they improve accuracy for real fluids, especially near critical conditions and across wider ranges of temperature and pressure. Now we proceed to slide 20, titled Beyond van der Waals, Why More EOS Exist. This slide is a reality check, and it is also a professional lesson. Van der Waals is historically important and conceptually beautiful, because it introduces physical corrections and can even predict critical constants. But in real engineering and real thermodynamic calculations, accuracy matters. This slide explains why van der Waals can be inaccurate and why more sophisticated equations of state were developed and are commonly used in practice. By the end of this slide, you should be able to do three things. First, you should be able to state the main limitations of the van der Waals equation in plain physical terms. Second, you should be able to recognize the names of common improved cubic equations of state used in practice. Third, you should be able to explain the key message: choosing an equation of state is a decision based on required accuracy and operating conditions, not a matter of personal preference. Let us start with the heading on the slide, Limitations and Common Improvements. That tells you the structure. First we diagnose what can go wrong with van der Waals, then we mention typical improved models. Now, Under why van der Waals can be inaccurate, the slide gives two key points. The first point says, it is a mean field model, with a simple attraction term and simple excluded volume. Let us interpret mean field in a way that is useful for you. It means the model treats the effect of attractions in an averaged, simplified way, rather than capturing the detailed molecular structure of interactions for different substances. The attraction term is proportional to A and to the square of density, and the excluded volume is represented by a single parameter B. Those are physically meaningful, but they are not detailed enough to capture all differences among real fluids, such as molecular shape, polarity, hydrogen bonding, and complex intermolecular potentials. So, van der Waals often captures the trend correctly, but the numbers can be off. The second point says, it can be poor near the critical region and for liquid densities. This is also a very important statement. Near the critical region, properties change rapidly and real fluids exhibit complex behavior, including strong fluctuations. A simple model like van der Waals often fails to match accurate experimental data in that region. For liquid densities, the fluid is very dense, and the assumptions behind simple corrections can break down. Excluded volume effects, short-range structure, and non-ideal interactions become highly significant. So, van der Waals can struggle to predict liquid phase properties accurately. Now, based on these limitations, the slide introduces common improved cubic EOS used in practice. It lists three families: Redlich, Kwong, Soave, Redlich, Kwong, and Peng, Robinson. I want you to see the pattern. These are all still called cubic equations of state, meaning that when you write them in terms of molar volume, the resulting algebra often leads to a cubic equation. They preserve some of the simplicity and computational convenience of van der Waals type forms, but they modify the attraction term and sometimes the temperature dependence to fit real fluid behavior better. The slide lists Redlich, Kwong, abbreviated RK. Soave, Redlich, Kwong, abbreviated SRK. Peng, Robinson, abbreviated PR. At this stage, the slide does not show the explicit equations, so we will not invent them here. The safe conclusion is simply, these are common improved cubic equations of state that are widely used because they often provide better accuracy than van der Waals for many practical conditions. Now, focus on the final line. Key message: choose an EOS based on accuracy needs and conditions, pressure, temperature, mixture versus pure. This sentence is the professional takeaway. What does it mean in practice? It means you do not choose an equation of state because it is the first one you learned. You choose it based on what you need to predict and in what regime you operate. If you are working at low pressure and far from condensation, an ideal gas model or a simple correction might be sufficient. If you are working near critical conditions, high pressure, or liquid-like densities, you may need a more sophisticated equation of state. If you are dealing with mixtures, the choice becomes even more important because mixing rules and interaction parameters can dominate prediction quality. So, accuracy needs and conditions is a reminder that the equation is a tool, and tool choice must match the job. Now let us do a checkpoint. I want you to answer these questions mentally. First, why can van der Waals be inaccurate? You should be able to say, it is a simplified mean field model with simple attraction and excluded volume terms, and it can perform poorly near the critical region and for liquid densities. Second, can you name at least two improved cubic equations of state listed on this slide? You should be able to say, Redlich, Kwong, Soave, Redlich, Kwong, and Peng, Robinson. Third, what is the key message about choosing an equation of state? You should be able to say, choose based on accuracy requirements and operating conditions, including pressure, temperature, and whether the system is a mixture or a pure fluid. Let me summarize this slide. Van der Waals is valuable for physical insight and for illustrating how an equation of state can predict critical constants, but it can be inaccurate because it is a simplified mean field model with basic attraction and excluded volume terms. It often performs poorly near the critical region and for liquid densities. Therefore, more accurate cubic equations of state are commonly used in practice, such as Redlich, Kwong, Soave, Redlich, Kwong, and Peng, Robinson. The key lesson is that an equation of state should be chosen based on the required accuracy and the specific conditions of the problem, including pressure, temperature, and mixture versus pure fluid behavior. Now we transition to the next slide. Next, we will apply what we have learned in a worked example, where we compare an ideal gas calculation with a real gas calculation using an equation of state, so you can see the practical impact of non-ideality in numbers and workflow. Now we proceed to slide 21, titled Worked Example, Ideal Gas versus van der Waals. This slide is designed to make the real gas discussion feel concrete. Until now, we have talked about Z, virial, and van der Waals as concepts and models. Here, we actually compute a pressure in two ways and compare the results. By the end of this slide, you should be able to do the following. You should be able to set up an ideal gas calculation for pressure. You should be able to set up a van der Waals calculation for pressure using the given A and B constants. And you should be able to interpret, physically, why the two answers are not identical. Let me begin by reading the problem statement carefully, because the problem setup already contains the key information you need to choose the correct equations and units. The slide says, a 4.25-liter flask contains 3.46 moles of CO2 at 229 degrees Celsius. Compute the pressure using, Part A, ideal gas law, and Part B, van der Waals equation of state. Then it tells you the constants you must use. It says, use R equals 0.082057 liter atmosphere per mole per Kelvin. And for CO2, use A equals 3.59 liters squared atmosphere per mole squared, and B equals 0.0427 liter per mole. I want you to notice something immediately. The gas constant R is given in liter atmosphere per mole per Kelvin. That means if you keep volume in liters and temperature in Kelvin, the resulting pressure will come out in atmosphere. So unit consistency is already built into the problem. Now, I will guide you through the solution in two parallel tracks, first the ideal gas solution, then the van der Waals solution. While doing this, I want you to constantly ask, which physical effects does each model include, and which does it ignore? Let us start with solution part A, ideal gas. Step 1 is temperature conversion. The slide explicitly shows T equals 229 plus 273.15 equals 502.15 Kelvin. Please remember this as a habit. When you use the ideal gas law, you must use absolute temperature, in Kelvin. So we convert 229 degrees Celsius into 502.15 Kelvin. Step 2 is applying the ideal gas law in the pressure form. P equals nRT divided by V. Here, N is 3.46 moles. R is 0.082057 liter atmosphere per mole per Kelvin. T is 502.15 Kelvin. And V is 4.25 liters. When you substitute those values into P equals nRT over V, the slide shows the result. P equals 33.55 atmosphere. So, according to the ideal gas law, the predicted pressure in this flask is 33.55 atmosphere. Now pause. Before we even do van der Waals, I want you to interpret what this means. 33.55 atmosphere is not a tiny pressure. It is significantly above 1 atmosphere. That is already a hint that real gas effects could matter, because we are not in a very dilute, low-pressure regime. However, whether they matter a little or a lot depends on the balance between attractions and excluded volume effects. That is exactly what the van der Waals calculation will show. Now let us move to solution part B, van der Waals. The slide tells you which form of the van der Waals equation to use for pressure. P equals nRT divided by V minus NB, minus A times N over V squared. I want you to read it slowly, because it contains two corrections that reflect the two physical failures of the ideal gas model. The term V minus NB is the volume correction. It says the free volume available for molecular motion is smaller than the container volume because molecules have finite size. This correction tends to increase pressure, because the denominator becomes smaller. The term A times N over V squared is the attraction correction, and it is subtracted. Attractions reduce the measured pressure because they reduce wall impacts. This correction tends to decrease pressure. So van der Waals does two things at the same time: it pushes pressure up through the volume correction, and it pulls pressure down through the attraction correction. The final answer depends on which effect wins. Now follow the slide step-by-step numbers. First, compute V minus NB. V is 4.25 liters. N is 3.46 moles. B is 0.0427 liter per mole. So NB equals 3.46 times 0.0427. The slide then shows V minus NB equals 4.25 minus that product equals 4.102 liters. So the effective free volume is 4.102 liters, which is slightly smaller than the original 4.25 liters. That is the excluded volume effect. Second, compute the attraction term. A times N over V squared. Here, A is 3.59 liters squared atmosphere per mole squared. N over V is 3.46 divided by 4.25, and then squared. The slide shows the numerical value of this attraction correction as 2.39 atmosphere. So, according to van der Waals, attractions reduce the pressure by about 2.39 atmosphere under these conditions. Now we combine both pieces in the full expression for pressure. P equals nRT over V minus NB, minus the attraction correction. The slide shows P equals the same numerator, nRT, divided by 4.102, minus 2.39, giving P equals 32.37 atmosphere. So the van der Waals prediction is 32.37 atmosphere. Now, let us compare the two results clearly. Ideal gas, 33.55 atmosphere. Van der Waals, 32.37 atmosphere. The van der Waals value is slightly lower. And the slide gives a short interpretation at the bottom. Van der Waals predicts a slightly lower pressure because attractions reduce wall impacts. I want you to internalize that interpretation, but I also want you to understand why the result is only slightly lower, not dramatically lower. In van der Waals, the volume correction, V minus NB, makes the effective volume smaller. That tends to increase the pressure compared with the ideal gas calculation, because you are dividing by a smaller volume. But the attraction term subtracts a pressure amount, 2.39 atmosphere, which pushes the pressure down. In this particular problem, the attraction effect dominates enough that the final pressure is lower than the ideal gas prediction. So, the key learning outcome from this worked example is not only the two final numbers. The key learning outcome is the competition of two physical effects. Finite molecular size reduces free volume, which pushes pressure up. Intermolecular attractions reduce wall impacts, which pushes pressure down. Van der Waals incorporates both effects explicitly, while the ideal gas law incorporates neither. Now let us do a checkpoint, because this is exactly the kind of reasoning that appears in exams. First checkpoint: if you forget to convert 229 degrees Celsius to Kelvin, your pressure will be wrong, because the ideal gas law requires absolute temperature. So always convert to Kelvin. Second checkpoint: in van der Waals, do not replace V by V minus NB everywhere. The attraction correction uses N over V squared, as shown on the slide, so you must follow the exact form given. Third checkpoint: think about the sign. The attraction term is subtracted. That means stronger attractions, or higher density, will reduce pressure more strongly in this model. Now I will give you a short mini summary. This slide shows a real numerical comparison. Using P equals nRT over V, the ideal gas law predicts 33.55 atmosphere. Using van der Waals, P equals nRT over V minus nB, minus A times n over V squared, the pressure becomes 32.37 atmosphere. The van der Waals pressure is slightly lower because the attraction correction reduces wall impacts and therefore reduces measured pressure. Now we transition to the next slide. Next, we will shift from calculation to conceptual accuracy and common misconceptions, so you can avoid typical errors when interpreting critical behavior, Z, and equations of state in problem settings. Now we proceed to slide 22, titled Common Misconceptions, Exam Traps. This slide is not about adding new formulas. It is about protecting your understanding from the most common incorrect shortcuts. In real gas topics, many errors come from mixing up definitions, confusing phase concepts, and ignoring units. So, on this slide, I want you to slow down and treat each statement as something you might hear in a classroom discussion or see in an exam option. Your job is to recognize why it is wrong and what the correct reasoning is. By the end of the slide, you should be able to do two things. First, you should be able to explain why each incorrect statement is incorrect, using precise thermodynamic reasoning. Second, you should be able to state the correct concept in a clean, exam-ready way. Let us go through the slide line by line. The slide says, be careful with these statements, and then it lists 4 common traps. Trap number 1, critical point equals boiling point. The slide marks this as incorrect, and it gives the correction, boiling point depends on pressure, while the critical point is unique, defined by T sub C and P sub C. Let me explain that carefully. A boiling point is not a single universal temperature for a substance. It is defined at a specific pressure. For example, normal boiling point is the boiling temperature at 1 atmosphere. If you change the pressure, the boiling temperature changes. That is why boiling points shift in a pressure cooker or at high altitude. In contrast, the critical point is a unique thermodynamic point where the liquid-vapor boundary ends. It is defined by a unique pair of values, T sub C and P sub C, and also a corresponding V sub C. It is not boiling at some pressure. It is the termination of the coexistence curve itself. So the correct statement you should remember is, boiling point is a point on the liquid-vapor boundary at a specified pressure, while the critical point is the end point of that boundary. Trap number 2, above T sub C, increasing pressure will always produce liquid. The slide marks this as incorrect, and it gives the correction, above T sub C there is no liquid-vapor boundary. This is one of the most important conceptual rules in this topic. Above the critical temperature, you cannot cross into a distinct liquid phase by pressure alone because the boundary line has ended. What you get instead is a continuous change in density and properties within a single phase. So, even if pressure is extremely high, if temperature is above T sub C, you do not get a separate liquid phase separated by a meniscus. The correct statement is, above T sub C, compression does not produce a liquid-vapor phase transition, it produces a single supercritical fluid state with continuously varying properties. Trap number 3, Z less than 1 always means low pressure. The slide marks this as incorrect, and it gives the correction, Z depends on both temperature and pressure, and attractions can dominate at moderate pressure. Let us unpack that. Z less than 1 means attractions dominate relative to the ideal gas prediction, which can happen at moderate pressures depending on the substance and temperature. It is not restricted to low pressure. In fact, at extremely low pressure, many gases approach ideal behavior, meaning Z approaches 1, not necessarily less than 1. The dip below 1 often occurs at intermediate pressures where attractions are noticeable but crowding is not yet dominating. So the correct statement is, Z depends on both P and T, and the sign of deviation reflects whether attractions or repulsions dominate under those conditions, not simply whether pressure is low or high. Trap number 4, unit consistency is optional. The slide marks this as incorrect and gives the correction, always keep R consistent with P and V units. This is a purely practical trap, but it causes many wrong answers. The gas constant R has different numerical values depending on the unit system. If you use R equals 0.082057 liter atmosphere per mole per Kelvin, then your volume must be in liters and your pressure will come out in atmosphere. If you instead use R in joule per mole per Kelvin, then pressure and volume must be consistent with Pascal and cubic meter, because 1 joule equals 1 Pascal times 1 cubic meter. So the correct habit is, choose a unit system first, then choose the matching value of R, and keep all quantities consistent. Unit inconsistency is not a small mistake. It can change your answer by large factors. Now, let us do a checkpoint. I want you to test yourself by correcting each incorrect statement in one sentence. First, replace critical point equals boiling point with the correct sentence. Boiling point is pressure dependent and lies on the liquid, vapor boundary, while the critical point is the unique termination of that boundary at T sub C and P sub C. Second, replace above T sub C, increasing pressure will always produce liquid with the correct sentence. Above T sub C there is no liquid, vapor phase boundary, so compression alone cannot create a distinct liquid phase. Third, replace Z less than 1 always means low pressure with the correct sentence. Z depends on both temperature and pressure, and Z less than 1 indicates attraction-dominated non-ideality, which can occur at moderate pressure depending on conditions. Fourth, replace unit consistency is optional with the correct sentence. Unit consistency is mandatory, and the value of R must match the units of pressure and volume. Let me summarize this slide. This slide highlights 4 common misconceptions. The critical point is not the boiling point because boiling depends on pressure, while the critical point is a unique state defined by T sub C and P sub C. Above T sub C, increasing pressure does not necessarily produce a liquid because the liquid, vapor boundary does not exist above the critical temperature. Z less than 1 does not automatically mean low pressure because Z depends on both temperature and pressure and reflects whether attractions dominate. And unit consistency is never optional, R must be consistent with the chosen pressure and volume units. Now we transition to the next slide. Next, we will consolidate the lecture into a summary of key equations and key takeaways, so you have a clean mental formula bank and a clear conceptual storyline from ideal gas limits, to critical properties, to Z, to equations of state. Now we proceed to slide 23, titled Summary and Key Equations. This slide is your consolidation slide. It is where I want you to mentally close the loop of the entire lecture, from why the ideal gas law fails, to what critical properties mean, to how we correct real gas calculations using Z, and finally to how equations of state encode those corrections in different ways. By the end of the slide, you should be able to do 2 things. First, you should be able to retell the lecture storyline in a short, coherent summary. Second, you should be able to recognize and correctly use the must-know equations on the right side, including how to read them out loud and what each one is used for. Let us begin with the left panel, Key Takeaways. I will take each point and briefly connect it to what we already learned. First takeaway, ideal gas works best at low pressure and high temperature. This is our decision rule. Low pressure means low density, so molecules are far apart and both finite size effects and intermolecular forces become less significant. High temperature means thermal motion dominates, making attractions relatively less important. So, under those conditions, PV equals nRT becomes a reliable approximation. Second takeaway, real gas deviations come from finite size plus intermolecular forces. This is the core physical origin. Finite size reduces the free volume available for motion, and intermolecular forces, especially attractions, change the measured pressure by changing wall impacts and by enabling condensation behavior. Third takeaway, the critical point ends the liquid, vapor boundary, and above T sub C the fluid is supercritical. This is the phase behavior heart of the lecture. The critical point is where liquid and vapor become indistinguishable, the interface disappears, and above the critical temperature there is no liquid, vapor boundary to cross. Fourth takeaway, the Z factor provides a practical correction, PV equals Z nRT. This is the operational bridge between ideal gas calculations and real gas behavior. Z captures the deviation from ideality as a single dimensionless factor. Fifth takeaway, the virial equation of state is a controlled low-density expansion. This means it represents Z as a series in 1 over V sub m, where the correction terms are organized by interaction complexity and become small in the dilute limit. Sixth takeaway, the van der Waals equation of state provides physical corrections, A and B, and it predicts critical constants. Here, A represents attraction strength, B represents excluded volume per mole, and the model can generate expressions for V sub C, T sub C, and P sub C, though with known limitations. Now, move to the right panel, Formula Bank, must know. This is the part I want you to treat like a toolbox. Every equation shown here has a purpose, and you should know when to use which one. At the top, you see the ideal gas law. PV equals nRT. Read it clearly, P times V equals N times R times T. This is your baseline model for dilute gases. Next, you see the definition of Z. Z equals PV sub M over RT. Read it, Z equals P times V sub M over R times T. This is the definition that tells you what Z means and how it is computed from state properties. Next, you see the corrected real gas form. PV equals Z nRT. Read it, P times V equals Z times N times R times T. This is the practical correction form. When you have Z, you can solve for V, P, or N using the same algebra you already know from ideal gas problems. Next, you see the virial expansion. Z equals 1 plus B of T over V sub M plus C of T over V sub M squared, plus ... Read it, Z equals 1 plus B of T divided by V sub M, plus C of T divided by V sub M squared, plus ... This is the equation you use when you want a controlled low-density representation of non-ideality. It is most reliable in single-phase, dilute conditions. Next, you see the van der Waals equation in its combined correction form. Open parenthesis P plus A times open parenthesis N over V close parenthesis squared close parenthesis, times open parenthesis V minus NB close parenthesis, equals nRT. Read it slowly. Open parenthesis P plus A times open parenthesis N over V close parenthesis squared close parenthesis, times open parenthesis V minus N times B close parenthesis, equals N times R times T. This is a physically motivated cubic equation of state that corrects both pressure and volume. Finally, at the bottom, you see the predicted critical constants from the van der Waals model. V sub C equals 3B. T sub C equals 8 A over 27 RB. P sub C equals A over 27B squared. These are the model's predictions obtained from the inflection point conditions on the critical isotherm. They are important because they show how a model equation of state can generate critical properties, which the ideal gas law cannot. Now I want you to do a very short checkpoint. If you are given a gas at low pressure and high temperature, which equation is your first choice? It is PV equals nRT, the ideal gas law. If you suspect non-ideality, what is your next step conceptually? You move toward Z and write PV equals Z nRT, then you estimate Z using reduced properties and charts or an equation of state. If the problem states low density and single phase and asks you to think in terms of interaction corrections, which model is most appropriate? The virial expansion. If the problem asks you to incorporate finite size and attractions explicitly with A and B constants, which model do you use? The van der Waals equation. Now, let me summarize the slide in a compact way. The lecture's storyline is, ideal gas behavior is a low-pressure, high-temperature approximation. Real gases deviate because molecules have finite size and intermolecular forces. The critical point marks the end of the liquid-vapor boundary and introduces supercritical behavior. Z quantifies non-ideality and corrects the ideal gas law through PV equals Z nRT. The virial equation provides a controlled low-density series for Z, and the van der Waals equation introduces physical corrections with parameters A and B and can predict critical constants, though with limitations. Now we transition to the next slide. Next, we will do a quick concept check, where you will test whether you can apply the core ideas, not only recall the equations. I will guide you through short questions that target the most important conceptual connections. Now we proceed to slide 24, titled Quick Concept Check, in class. This slide is designed to test whether you can express the most important ideas clearly in a short, exam-ready way. The instruction on the slide is to answer briefly, 1 to 2 sentences each. So, I will model exactly that style, but I will also guide you on what an examiner is really looking for in each answer. Let us go question by question. Question 1, what does Z less than 1 mean physically? A strong answer is, Z less than 1 means the real gas has P times V sub m smaller than R times T under the given conditions, so attractions dominate and the gas is more compressible than the ideal gas prediction. Question 2, why can't a gas be liquefied by pressure alone when T is greater than T sub C? A strong answer is, above the critical temperature there is no liquid-vapor phase boundary to cross, so compression changes density continuously but does not produce a distinct liquid phase. Question 3, in van der Waals EOS, which parameter represents attractions, and which represents excluded volume? A strong answer is, A represents attraction strength and B represents excluded volume per mole, meaning finite molecular size. Question 4, under what conditions is the ideal gas law most reliable? A strong answer is, the ideal gas law is most reliable at low pressure and high temperature, where the gas is dilute and intermolecular forces and finite size effects are minimal. Now, I want you to do a quick self-check. For each answer, you should notice that you use the correct keywords, attractions versus repulsions, phase boundary, critical temperature, and low pressure high temperature. Those are the anchor concepts. Let me summarize the slide in one sentence. This slide asks you to demonstrate that you can connect definitions to physical meaning, Z to intermolecular forces, T sub C to phase boundaries, A and B to attractions and excluded volume, and ideal gas reliability to low pressure and high temperature. Now we transition to the next slide. Next, we will move into practice problems and homework style tasks, where you will apply these ideas in longer calculations and structured problem-solving workflows. Now we proceed to slide 25, titled Practice Problems, Homework. This slide is your bridge from lecture understanding to mastery. The key idea is simple: you do not truly learn real gas behavior by reading definitions once. You learn it by repeating the workflow, using correct units, stating assumptions clearly, and interpreting the physics behind the numbers. By the end of the slide, you should clearly understand what you are expected to submit, how to structure your solutions, and what kind of thinking you should demonstrate in each problem. I will guide you through each task and explain what it is testing. Let us start on the left panel. Do these to master the topic. There are 3 homework tasks. Homework task 1 is for CO2 at temperature 350 Kelvin and pressure 10 megapascal. It has 3 subparts, A, B, and C. This problem is designed to test your corresponding states plus Z workflow. Part A says, compute T sub R and P sub R using NIST critical constants. So here, you must look up, or use the provided critical constants in your reference, for CO2, T sub C and P sub C. Then you compute reduced temperature as T sub R equals T over T sub C, and reduced pressure as P sub R equals P over P sub C. This checks whether you can normalize the state correctly and whether you remember to keep temperature in Kelvin and pressure units consistent. Part B says, estimate Z from a generalized chart. This checks whether you can use the reduced variables in the correct direction. You locate your P sub R on the horizontal axis, select the curve corresponding to your T sub R, and read Z from the vertical axis. If your T sub R falls between curves, you should state that you interpolate conceptually and explain your estimate clearly. The slide does not give detailed interpolation rules, so your responsibility is to make the estimate transparent. Part C says, compute V sub m equals ZRT over P. This checks whether you can apply the corrected real gas relation to compute molar volume. The important point here is unit discipline. If P is in Pascal, then R should be in joule per mole per Kelvin and V sub m will come out in cubic meter per mole. If you use megapascal, you must still ensure R and the resulting volume units are consistent. So, this part tests both conceptual workflow and unit consistency. Now, homework task 2 says, using van der Waals equation of state, compare pressure ideal versus pressure van der Waals for N equals 1.00 mole N2, V equals 1.0 liter, and T equals 300 Kelvin. It also instructs, use A and B from a data table. This problem is designed to test whether you can execute a side-by-side comparison of ideal and van der Waals and interpret the difference. You will compute P ideal using P equals nRT over V, with consistent units. Then you will compute P van der Waals using the form shown earlier in the lecture, P equals nRT over V minus NB, minus A times N over V squared. Because this is N2, you must obtain the correct A and B constants from a reliable table. The slide does not provide those values, so you must not invent them. The key is to show you know where A and B enter and what they mean physically. B reduces free volume, pushing pressure up, while A reduces measured pressure, pushing pressure down. Your final comparison should include a short statement about which effect dominates under the given conditions. Now, homework task 3 is conceptual. Explain why Z approaches 1 as pressure approaches 0 for any gas. This question is designed to test your physical reasoning, not your algebra. A strong explanation is, as pressure approaches 0, the gas becomes extremely dilute, meaning molecules are far apart and intermolecular interactions become negligible. Finite size effects also become negligible because the occupied volume is tiny compared to the container volume. In that dilute limit, real gas behavior approaches the ideal gas model, so PV sub m approaches RT and therefore Z approaches 1. Now move to the right panel, submission checklist. This is the part that tells you exactly how your homework will be evaluated. It lists 5 items, and I want you to follow them like a template. First, show units. That means every given value and every computed value must carry units. If you switch unit systems, you must state it clearly. Second, state assumptions. For example, if you assume an approximate Z reading from a chart, state that you are estimating and indicate the approximate T sub R curve used. If you assume interpolation, state it. If you assume single-phase behavior, state it. Third, show steps, not just the final formula. That means you must write the workflow, compute T sub R and P sub R, read Z, then compute V sub m. Or compute ideal pressure, then compute van der Waals pressure with intermediate quantities such as V minus NB and the attraction correction term. Fourth, box your final answer. That means clearly highlight the final numerical result for each requested quantity, so it is easy to identify. Fifth, provide a brief physical interpretation. That means 1 or 2 sentences explaining whether the gas is more or less ideal, whether attractions or repulsions dominate, or why the corrected value differs from the ideal value. Now let us do a checkpoint so you can immediately see the intended structure. For problem 1, your output should look like, given T and P, compute T sub R and P sub R with units, estimate Z from the chart, compute V sub M using V sub M equals ZRT over P, then write one sentence about what your Z value implies physically. For problem 2, your output should show P ideal and P van der Waals, then a short statement about whether van der Waals is higher or lower and why. For problem 3, your output should be a short conceptual paragraph with clear reasoning about the dilute limit. Let me summarize this slide. This slide assigns 3 practice tasks, a corresponding states Z workflow for CO2 at specified T and P, a direct ideal versus van der Waals pressure comparison for N2 using tabulated A and B, and a conceptual explanation of why Z approaches 1 as pressure approaches 0. Your submission must show units, state assumptions, show steps, box final answers, and include brief physical interpretation. Now we transition to the next slide. Next, we will move to the contact and closing information, and I will give you final guidance on how to approach the homework efficiently and correctly, so you build both calculation accuracy and strong physical intuition. Now we proceed to slide 26, which is the contact slide. This slide has a simple purpose, but it is still part of the learning process. It tells you how to reach me if you need clarification, if you want to discuss the homework, or if you want to explore the topic beyond what we covered in today's lecture. I want you to view this as an invitation to communicate academically and professionally. Let me connect the slide to the previous one. In the last slide, I assigned practice problems and I gave you a submission checklist, show units, state assumptions, show steps, box the final answer, and provide a brief physical interpretation. If you apply that checklist carefully and you still find a specific step confusing, then that is the right moment to contact me, with a precise question. For example, you should not simply say, "I do not understand Z." Instead, you should say, "I computed T sub R and P sub R, but I am unsure how to read Z from the generalized chart at my P sub R value, or I am confused about unit consistency when using megapascal with R." Now, please look at the top banner. It says, "Contact, Dr. Heri Septya Kusuma." The slide then lists several contact channels. First, there is WhatsApp, with the number +6 285730780240. This is the most direct channel for urgent academic communication, such as short clarifications about lecture content, homework instructions, or scheduling. Second, there is Instagram, listed as Heri Kusuma, with the handle @Heri Septya Kusuma. This is a channel where academic updates and communication may also be shared, and you can use it to stay connected with course-related announcements if needed. Third, there is Facebook, listed as Heri Kusuma, with the link shown on the slide. This is another social channel, and it may also contain academic and professional updates. Fourth, there is ResearchGate, with the profile link shown on the slide. This is a research-focused platform. If you want to explore my publications, research activities, or academic materials, ResearchGate is an appropriate place. It is also useful if you want to learn how scientific communication is done in practice, beyond the classroom. Now, I want to give you a brief guidance on how to communicate effectively when you contact me, because this will save your time and it will improve the quality of the help you receive. When you ask a technical question, always include the following 3 items in your message. First, state the problem number and what you are trying to find, for example homework problem 1, Part C, compute V sub m. Second, show what you have already done, at least the key intermediate values, for example your computed T sub r, P sub r, and your estimated Z. Third, state exactly where you are stuck, for example I am unsure which unit system to use for R when pressure is in megapascal. If you do this, the discussion becomes efficient and academically meaningful. Now, let me also set a final expectation. The goal is not only to obtain the correct numerical answers. The goal is to build a correct way of thinking, choosing the appropriate model, stating assumptions, maintaining unit consistency, and interpreting the physical meaning of the result. If you communicate with me using that structure, you are already practicing the mindset of a professional scientist or engineer. Let me summarize this slide. This slide provides my contact information through WhatsApp, Instagram, Facebook, and ResearchGate. Use these channels to ask focused questions, especially when you have followed the workflow and checklist but still need clarification. When you contact me, state the problem, show your steps, and specify exactly what you do not understand, so the response can be precise and helpful. Now we transition to the final slide. Next, we will close the lecture with a short wrap-up, reinforce the key message one last time, and I will give you final instructions on how to approach the homework and prepare for assessments on this topic. Now we proceed to the final slide, slide 27, which is the closing slide. The slide says Terima kasih, and it also includes the phrase Matur nuwun, which is a respectful local expression of gratitude. In this closing, I will wrap up the lecture in a clear way, reinforce the key learning message, and give you final directions on what you should do next so that this topic becomes something you truly master, not something you only heard once. Before we close, let me remind you of the storyline of today's lecture in a compact and connected way. We began with a fundamental point, the ideal gas law, P times V equals N times R times T, is a powerful model, but it has assumptions. It works best when the gas is dilute and thermal motion dominates, which typically means low pressure and high temperature. Then we identified the two physical reasons real gases deviate from ideal behavior: molecules have finite size, and molecules experience intermolecular forces. Those two facts are not small details. They are exactly the reason phase boundaries exist and exactly the reason a critical point exists. Next, we built the phase behavior foundation using the P-T diagram and P-V isotherms. You learned that the liquid-vapor boundary terminates at the critical point, and above the critical temperature, T sub C, a gas cannot be liquefied by pressure alone. You also learned the physical meaning of the critical point: liquid and vapor become indistinguishable and the interface disappears, and near the critical point you may observe critical opalescence. After the concept was clear, we moved into tools. We defined the critical constants T sub C, P sub C, and V sub C, and we used them to create reduced variables, T sub R equals T over T sub C and P sub R equals P over P sub C. This gave you a systematic way to compare different substances through corresponding states. Then we introduced the compressibility factor Z as Z equals P times V sub M over R times T, and we showed how it becomes a practical correction factor through PV equals Z N RT. You learned how to interpret Z equals 1 is ideal, Z less than 1 often indicates attraction-dominated behavior, and Z greater than 1 often indicates repulsion and finite size dominance. You also learned the workflow: compute T sub R and P sub R, estimate Z from a generalized chart or compute it from an equation of state, then correct your calculation using Z. Then we went deeper into equations of state. We discussed the virial equation as a controlled low-density expansion and saw why truncation involves assumptions about density and proximity to phase change. We then constructed the van der Waals equation with physical corrections for volume and pressure, interpreted A and B, and even derived the predicted critical constants from van der Waals using the critical point inflection conditions. Finally, we emphasized that van der Waals has limitations and that more accurate cubic equations of state exist in practice, so model choice depends on required accuracy and operating conditions. Now, here is what I want you to do after this lecture, because this is where learning becomes real. First, reread the summary slide and make sure you can explain, in your own words, what the critical point means physically and why it ends the liquid-vapor boundary. Second, practice the workflow at least once, compute reduced variables, estimate z, and use v sub m equals zRt over p. Third, work through the homework problems carefully with the submission checklist in mind. Show units, state assumptions, show steps, box your final answer, and provide a brief physical interpretation. If you do those 4 things consistently, your understanding will become stable and exam ready. Let me also give you one final exam mindset reminder. Most mistakes in this topic come from rushed shortcuts, forgetting Kelvin, mixing units for R, confusing boiling point with critical point, or assuming that above T sub C compression must create liquid. If you slow down and follow the workflow, those mistakes disappear. So, once again, thank you. Terima kasih. Maturnuwun. I appreciate your attention and your effort. Please proceed with the practice problems, and if you need clarification, use the contact channels provided earlier and communicate with a precise question and your working steps. I will see you in our next session.